we've all had enough caffeine, woken up. So thank you for joining us. Thanks to Mooli and the rest of the team, the organizing team, the volunteers for kicking off yet another fantastic DSS, starting with DSS 101. So hopefully we're all here to learn and get better. And who's here not into finding bugs? Okay, maybe a couple, but all of us are into finding and fixing bugs. So this is a topic that you're going to be hearing from the four of us here today. And no guesses for why this is 42 tips, but we are 4 security researchers. So why do we want to do this, right? Obviously, because Vitalik says so. Just kidding, but this is a tweet. I mean, this is sort of representative. I mean, we hear a lot about scaling in Ethereum, right? We hear the hundreds and thousands of L2s. But for all of us, the security researchers here, we know that hacks, scams, rug pulls happen on a daily basis. And that's why we are here, to find the bugs, fix the bugs, make the space safer, more reputable, and and generally good for the whole ecosystem. So yeah, as this tweet says, I mean, this, I don't know if Vitalik was referring to the dApp layer, the applications, but presumably Ethereum layer 1s and layer 2. So the technical risk in the bugs in code is something really, really high. We only see this when things go wrong. So unfortunately, that is an occupational risk or hazard that comes with information security. So all the security researchers here, you never really get to, well, it's sort of different in this industry because, whenever you participate in contests or other things and you find bugs, you're recognized. But in general, before Web3, people or corporates are generally in the limelight only when things go wrong. So, that's something changing in Web3. So that's what we're here to learn. And these numbers are really the smart contract hacks. And this is from DeFi Llama. These numbers have been going up. So as you can see the trend, I think the tallest bars were really the bridge hacks from hopefully a couple of years ago. And things sort of look better from this, but I don't think this paints a very accurate picture. So I don't think it accounts for all the user risk, the phishing, and so on. So this is, we want this to really sort of taper out, right? So that's why we are all here today. All right, so who are we? I am Rajiv. I've been a security researcher for a long, long time. Had a brief stint with Trail of Bits. That's when I got into Ethereum security, smart contract security around 2016. Participated as an early participant in many of the audit contests. But for a couple of years, I've been doing collaborative reviews as a lead security researcher at Spearbit Cantina. I'm also the founder of Securium, which is really known for its Ethereum security bootcamp and TrustX, the event. So that's me, but I'm here joined by my smarter colleagues, and we'll have them introduce themselves.
Hey everyone, I'm Nat. I'm also an independent security researcher. I've been doing security since 2020, where I also was at Trail of Bits. Before that, I was doing blockchain development. In the most recent years, I've been doing a lot of code review as well as invariant development. Horan.
Hey, my name is Johan, and I've been in the space for 6-7 years now. Been working on a lot of tools and tooling. Some of them you might know, some of them you might not. Started out kind of with Mithril, symbolic execution, and I won't bother you with all the others. I am also a somewhat active bounty hunter. I really enjoy it, and yeah.
Cool. And I am Hiccup, or Desmond, is my real name. I'm also an independent security researcher, joined the space in 2017. So it's really nice to be able to transit to Web3 security and help secure the space. Cool. And with that, we can start with our first 10 tips.
So the agenda is we have 42 tips. We're going to sort of split it up amongst the 4 of us. And at the very end, there is actually a workshop quiz, which should be very interesting. And it does have some rewards as well. So please stick around and yeah, have fun. Thanks.
Cool. Awesome. So let's get started with our first tip. It's about challenging your intuition and assumptions. And to kick things off, I'm going to make this a little interactive. So I need you guys to take out your phones and do the Slido. So let's have a little quiz to test some of our intuitions, okay? So do join, or you can just go to slido.com and key in the 7 digits that you see there. And I should start seeing your names pop up in the quiz section. And you can be anonymous and so on. Unfortunately, it's the free plan, so I only can allow up to 100 people to participate. So once I see that number, then I'll proceed on to the next slide. Awesome, awesome. The number's going up. Nice. I see some familiar names. All right, I'll give you guys maybe just another 20 seconds or so to join. And then, so it's just like a simple 3-question kind of thing to see how well you can challenge your intuition and understanding. Okay, I'll give another 5 seconds or so. 4, 3, come on, let's hit that number. Okay, and we're good. Okay, so first question, it's a statement, true or false, right? I recoup my losses, right? The meme coin I bought pumped 50% after it's down 50%. Is this a true or false? You have about 20 seconds to answer. Okay. Yeah. Oh, wow, good job. For those of you who answered false, that is correct, right? So if you work out the math, if let's say your coin that you bought is at $1, it goes down by 50%, it's at 50 cents, and goes up again by 50%, it's at 75 cents. It doesn't break even. So that's a simple warm-up question. And there's also like a timing, right? So if you can answer as fast as possible, then you'll be on top of the leaderboard. And just for fun. Okay, second question, right? So I am 31 years old, I'm introverted, relatively bright, and I majored in applied math. I'm deeply concerned with issues like front running and MEV, right? So which of the following is more probable? I am a security researcher, or I am a security researcher specializing in MEV. Which one would that be? Wow, okay, it's not too bad, not too bad. For those of you who chose the first option, that is correct. And why is that so? Because using basic probability theory, you'll know that the second category is a subset of the first. So just by that fact alone, the first is more probable. Right. Hey, Rajiv is first, and somebody is imitating me in second place. Cool. All right, last question. So a frog is stuck at the bottom of a well that's 5 meters deep. Each day, you know, it jumps up by 2 meters, but it slides down by a meter. So on what day is it able to jump out of the well? I mean, it's like 2, and then, you know, -1, and then, you know, just gotta work it out. And it might feel intuitive that, you know, maybe you might gravitate to an answer more than another, but we'll see. Okay. Not too bad, not too bad. And those of you who chose the fourth is correct. So if you work it out logically, it's an edge case, right, where on the 4th day, you're at 3 meters, the frog's at 3 meters. So it jumps 2 meters, it exits the well. It doesn't have to do that slide down by a meter. So it might seem that the 5th day is a bit more intuitive, but no, that's actually wrong. And so this kind of like gives you an idea of challenging what seems to be correct. It feels correct, but it may not necessarily be so, right? And congratulations to Desmond too. Awesome, wow, good job. Okay, so we're gonna look at a couple of real life examples that I kind of have experienced through my security reviews. And the first case is fee equivalence, right? So for instance, you can see these few lines of code. You have a swap fee, and usually indexes, you are able to specify either you're swapping the exact input or the exact output, right? So this is how the swap fee is calculated, right? You just take the fee in basis points, multiply by the specified amount, and if it's in exact or input or exact output, then you just subtract or add the swap fee, right? And this might seem to be correct, right? So as an example here, right, if I swap 100 USDC for DAI at parity 1-to-1, assuming the fee is at 1%, and I specify specify an exact input, right? So what does that mean? It means at 1%, it means I take 1 USDC as a fee, I should receive 99 DAI back, right? So the fee equivalence, in a sense, would be that if I specify 99 DAI as the exact output, I should be, the DEX should be requesting 100 USDC in return, right? And the problem is if you work through the math here, it doesn't really add up, right? 1% of the 99 DAI is only 0.99. So if you add that, you're missing by 1 cent. So you don't really have that exact equivalence. So what's the fix? Yeah, it's you kind of have to change the denominator a little bit, and that's the correct math. So again, it might seem, those few lines of code that you've seen previously might seem correct, but you kind of have to work out the math. And let's take a look at another example. Oh yeah, so if you work this out, then it would be correct. Let's take a look at another example, right, which is taking fees in shares. This is a Twitter thread by Xiaoming90, so just a credit to him. But taking fees in shares is quite common, right? Especially if you have auto-compounding vaults like ERC4626, right? So protocols tend to want to take fees in shares because it's auto-compounding. So the amount of fees that they get will increasingly accrue in value over time, right? So this is the formula that they use, right? So it's the harvest amount multiplied by the fee, and then multiplied by the total supply divided by the underlying value. So let's take an example, right? So say you have a 20% fee and you harvest 100 ETH, right? So technically the protocol should receive 20 ETH in fees. And let's work that out, right? So the harvest is 100 ETH, assuming we have a total asset initially of 1,000 ETH. So 100 ETH multiplied by the fee, which is 20%. The fee is specified in basis points. So then multiply by 100 shares, and you divide by 1,000. So yeah, just replacing the numbers with the variables, you'll see that the number of shares that are minted is 1.81, right? So the question is this 1.81 shares equivalent to 20 ETH, right? And you'll realize that it isn't, right? And so what's the reason behind it? Why is it that it's less than the 20 ETH that's expected? Well, if you think about it, you are actually diluting the share value because you're minting extra shares. So you have to account for that share dilution, right? And so this is kind of the correct formula that you are supposed to use instead. And if you work out the math, then you'll end up minting slightly a bit more shares, which will give the protocol the desired 20%, right? So again, something that looks really intuitive, it looks really correct, but then if you want to work out the math, it doesn't work out, right? So that is my first tip on challenging assumptions and challenging your intuition. Okay, so tip number 2, scrutinize the start and end of life cycles, right? Usually the start and end of life cycles are a bit more edge cases, right? So for instance, let's look at initialization, right? Is the condition for initialization explicitly defined? And if it's implicit, can it be exploited? And we've seen those happen in real life cases, right? The first is in Balancer v2, where I highlighted in red, you can see that there was an initial condition where you could exploit the case where the circulating supply is 0, right? And you cause the pool to be reinitialized by resetting the rate to 1. And the other is the meme attack that happened earlier this year, right, where the TLDR is that you're exploiting the initial condition of the 1-to-1 shares to value, the borrow share to asset ratio, right? So if you can get the system to a state where you have more shares equivalent to one way of value, then you can exploit that initial condition. So you do have to kind of take a look at the start of the life cycle and also consider the end of the life cycle, right? So is there any state that is supposed to be totally reset but isn't? And conversely, is there any that are not reset but they should be, right? So for instance, lingering approvals on token or ownership transfers. Okay, so this is a finding by WatchPark for a contest, a Sherlock contest, where they found that expired locks, like once you have if you know the V token model of locking out your tokens to receive more rewards, then once the lock expires, what is the state of that condition, right? And in this case, expired locks are considered the same as deposits with no locks, right? So there should be a way to kick out expired locks. Okay, so tip number 4, right? Be familiar with multiple frameworks, right? Foundry is mostly widely used, but there are projects that still use hard hat, right? So you might be spending time porting the setup, the logic over to Foundry, and that is kind of like a trade-off. And so it would be good to still be familiar with multiple frameworks like hard hat. But it could be worth it if you are using exclusive features that are only exclusive to that framework. So for instance, like invariant testing or fast testing might be more popular on Foundry. So then it might make sense to kind of port over the test suite from hard hat to Foundry. Okay, tip number 5, run coverage if possible. Unfortunately, more often than not, I run into the issue of stack to deep when I run with Foundry, even with the IR flag on. But if you can run it, it's a really good thing, especially if you pair it with coverage gutters, which is a useful extension, right? So if you run forge coverage you run this line, right? And then you turn on the extension, you can display the coverage. So you can see it will have 3 different colors, right? So green means the coverage, that line is covered. If you see yellow, it means either you're not fulfilling the entire coverage, you are missing out on the branch coverage. So it's either the if or the else branch that is not covered. And if you see totally red, then it's not covered at all, right? And if it's red, then those are prime areas you want to scrutinize those areas further, because that's where bugs might tend to lie more. Some other useful extensions like spell checker, the solidity extension by Nomic Foundation. So here, one example is that if you kind of like highlight over the function name, it kind of gives you the parameters and the variable types. The other useful extension is the solidity inspector, where it shows you, for instance, the contract size, and it shows you redundant imports, right? So you can see here it's an unused import, the console import there. Okay, tip number 7, you want to mock minimally, right? So as much as possible, you want to use actual implementations and network conditions, right? And the reason for this is that different networks have different behavior. So for instance, transient opcodes might still not be supported on some networks, or for instance, like solidity globals might return different values for different networks, right? So I would highly recommend doing fork tests, especially if the project that you are auditing is integrating with other projects. So for instance, like using RVADs, using the DSR, Maker's DSR, yeah. Okay, tip number 8, mess with the code. So you want to try re-implementing a certain function to differentiate against, right? And you might be able to spot some subtle differences. And you will start to question, like, why is it that I write things differently? And it might help you to uncover a subtle bug. And ideally, when you do the change, right, it should cause at least a test to fail. And that's kind of the idea of mutation testing, where you are kind of testing the strength of the test suite. Yeah, so if you notice, I went from tip number 2 to tip number 4, and that is where tip number 3 is. And it's the idea of thinking what is absent, right? So it's very easy to spot what's actually present, what you're actually seeing on screen. it's very easy to identify issues that are written rather than unwritten, right? Especially when you are reviewing fixes. And I feel that's where things tend to be a bit more tricky, right? So for instance, this was a PR that I reviewed for Uniswap v4, where they changed the v4 core, and you know, it looked good, LGTM, right? Turns out it's not really LGTM because there was something to be fixed in periphery that is dependent on this behavior, and that was a bug that I think some of you guys here in the room found as well. So you know, you live and learn, right? Yeah. Tip number 9, you want to periodically step away from the code base, right? And the thing is that you might suffer from review fatigue, where you're staring at the code like over and over again. Then you start to have tunnel vision, you suffer from cognitive biases. And that's when you might also start to realize that you see patterns that you're familiar with, and then that's when you start assuming things are correct. But you know, it might not necessarily be so. So consider like switching tasks. You might want to take a break, or you start writing some tests, or write up the issues that you found already. So just switching things up a little, mixing and matching a little bit, I think helps to keep your mind a little off. And then when you come back, it's in a way a fresher state of mind in a sense. So that would help you to be a little bit more focused. And it might help to open that part of your brain that spot something that you didn't see before. And for my last tip, it's about taking care of yourself, right? So you want to have, for instance, regular exercise. For me, I have a Garmin watch that I bought a few months ago to track my health, to track my sleep as well. So it's really important to take care of yourself physically, mentally, right? Touch grass, take a vacation, right? And I feel like this is like really important because if you want to be like athletes, you want to be at peak performance, it means you need to be at peak condition. So those are my 10 tips, and I'll hand it over to Horan. Thank you. Here you go.
Okay, so my background is, as I said before, in automated tooling, automated security analysis, but also in bug bounty hunting. And today I'm gonna kind of focus my tips on that second part, the bounty hunting, and not so much on tooling and using tooling. I think a few tips later on will cover those. And my first tip is has a little bit of overlap with the previous one. Take care of yourself. Pacing. On Twitter, sometimes you kind of get a sense that audit contests, bug bounty hunting, they're all about the grind sets and grinders. And I honestly believe that is like the worst possible approach to doing any kind of really good, deep security research. And I think like a couple of examples really outside of security research will show you that this kind of makes sense. So there's if you look at doctors, they also tend to have a culture around grinding, like taking multiple shifts, working really long hours, and not sleeping, that kind of stuff. And the data shows that more people die because of this. Like there's more risks that are introduced by like this type of grinding behavior. And I feel like, or I think the same is true for auditing or security research. This is like a very tough mental task that your brain is not able to do for like long stretches of time. Like you need to give your brain time to recover and digest. And to give an example, like I used to have a course in university. It was a while ago. And we had these challenges in this course where we got a day to solve some networking challenge. Like you built some kind of protocol, like it was very interesting. But for me, what those days looked like is me just going like tunnel vision for 4 hours until lunch, and then I'd take a walk to get my lunch. And during that walk, I solved the whole issue. Like I would be stuck for 4 hours basically, then 15 minutes walking, I solved it. So it's really important to give yourself or your brain like this time to rest and digest, to process, so you actually, work more optimally. So I think taking it easy is actually a more productive approach in the end. This is not to say that discipline isn't important, and also not to say that it's not a lot of work to like build the skill, build the knowledge necessary to do bounty hunting or security research, but just that when you're doing it 8 hours straight or doing more than 8 hours of reviewing code, I'm not sure that it will work well. Okay, tip 2. I think there's a lot of value in scoping out targets for bounty hunting. If you're like me, you have limited amounts of time available to do bounty hunting on a single target at a certain point in time. So for example, I'll have a week or a couple days. Then it doesn't make sense really to go for like an L2 implementation. Like it is just too large. So I think it makes sense to then pick targets that have about the size that you can handle or that you think you can find something interesting with the amount of time you have. Other things you can look for in finding bug or bounty programs to hunt on, or I guess audit contests, is the type of program. If you're very familiar with L2s, with bridges, then finding bugs in bridges and L2s is going to be easier. If you're not familiar with those, then it's going to take a lot more time, and you're going to be more efficient working on things that you're familiar with. That said, it's often like a good idea to switch things up to make sure you like stay sharp and everything. Then there's one more thing that's not really about you, but about the program itself. And this is something I kind of look for in bounty programs. It's the medium and high payouts. Because often a program will be like, here's a couple million for a critical bug, and then they won't pay out for highs. And this kind of tells me something about the mindset that people have running their bounty program, being not so much interested in improving their security, reducing risk of hacks, but more so kind of like catching just the worst case scenarios. I have the feeling that like even if you find something, you'll have a hard time getting a good payout out of those protocols. So I tend to look for that as well. Okay, tip 3. This kind of overlaps with my first tip a little bit. This actually kind of happened to me. So I was trying to sleep, lying in my bed, and then I'd spent the day like looking at some code, and my brain is like, yo, what happens if you liquidate your own position? And I was like, oh, shit. So in the middle of the night, I was typing up a bug report because, well, I couldn't sleep. And the tip here isn't really to try to sleep and then do bug bounty hunting at the same time. That's probably not a really good tip. But it's really about a mental model of the top idea on your mind. There's a blog post, I forgot where it was posted, but the idea is that you basically have like a place in your brain for a thing to work on when you're doing different things. So let's say I'm doing bounty hunting on a specific project, and then I'm gonna take a walk, or I'm gonna do the dishes, clean like the house, that kind of stuff. During that time, your brain is kind of like passively processing things, and so for me, like a not insignificant amount of bugs came from this passive processing time. So to really optimize on this, make sure that you're not trying to do too many things. Like if you bounty hunt and then do 2 hours of, I don't know, trying to learn something else, then your brain is wholly occupied with this other thing and not working on the bug bounty thing anymore. So if you just like make sure that you work on bounty hunting and then give your like brain, the passive processing time, that might work out really well for you. Okay. Then a tip on bug bounty discussions. Bug bounties are great, but unfortunately, if you submit a few, you'll probably get in a situation where the protocol team does not agree with you. It happens. Every discussion is different. Every team responds differently. It's usually a high-stakes situation, and you're telling someone, hey, your code doesn't work. Often, unintentionally, there's going to be fallacies. It makes sense to prepare for those fallacies in a way that you can handle them in a good way. Not just saying, hey, that's a fallacy, you don't know shit, but just handling it in such a way that you can move the conversation onwards. So there's a couple lists on the internet, you can look at them, be like, read through them, see how you should respond. It's a really good way to improve your speed, I guess, or improve your productiveness in these discussions. Another one thing you can do to improve these discussions is kind of change your mindset. I saw, like, over time I've seen tweets that kind of indicate like this adversarial mindset of like, this project sucks and they're not giving me anything. That usually doesn't work out really well. And I personally like to take a perspective of like, I want to work with this project in the future. I want to submit more bugs. I might want to work with them in a different capacity. So I adapt my self-communication to this. And that ends up being a lot more productive, or I think it ends up being a lot more productive than the more adversarial, hey, you need to pay me because X, Y, Z. Okay. Tip 16, diversify your skills. This is a somewhat cheesy one, but really anything you can learn outside of just Web3 security is going to be useful. So there's a couple lists here, like learning how compilers work can be super insanely useful because then you know how Solidity works, you can know about the quirks, like the issues that people might encounter. Everything becomes a lot more logical, and also like compilers in general make like your understanding of programming languages like insane. Another thing I really like is like don't stick to Web3 related topics necessarily. There's a book called How to Solve It. I'm not sure how to pronounce the author's name. It's a book about how to approach mathematics problems. There's like a strategy about like solving the issues and creating proofs. And I really like that because it kind of teaches you a different way to think about things. And the more ways you learn to think about things, like by learning about different topics, the more ways you can use to find actual bugs. So yeah, I think this is a very useful thing to do. Okay. Some specific bug hunting strategies. I think something that works really well is to find a specific paradigm and specialize in it. So for example, in DeFi, you have a lot of systems that allow you to have leverage. These systems have problems. Liquidation is usually very difficult to do right. And there's been tons of bugs there. So what you can do is kind of learn a lot about how these different systems work, what their pitfalls are, and then once you're really comfortable with them, you can probably just go on and Immunify list all the different like types of systems that might have leverage, go through all of them, and see if the pitfalls that you've identified or learned about are apparent in these implementations, and then, well, you report them, obviously, if they're there. So in DeFi, like leverage is one example. I think it makes sense to have a look at like what's like current, like a paradigm that is currently being developed, like concentrated liquidity is an example where there's like Uniswap released their version, and then like a couple other projects will also have like all implemented their concentrated liquidity. And if you were an expert, like you might have known that tick transitions and ending up like right on top of a tick and can be a really difficult thing to implement, which has led to some hacks, unfortunately. And like in that way, you might have gone through all the implementations and found issues related to that type of like difficulty in implementing this kind of paradigm. I think like ZK is an example where there's not that many people that I know of, at least, that are specialized in these kinds of systems. So there might be a lot of opportunity there. I don't know, not sure. But I think the general approach of finding paradigms, specializing, and then going broad can be very effective because you can go really quickly through a lot of bug bounty programs. Okay, that is kind of the go broad approach. There is also a go deep approach, and this is kind of the one I tend to follow. It works really well if you have like a very limited amount of time, which might be like a week or a weekend. And it's kind of like this explore, exploit type problem. So what I do is I kind of like explore a code base, or usually I just start reading documentation actually. And then I identify like points of interest or things that I think are going to be difficult. So it's really like it has some overlap with the paradigm and specialized strategy, in the sense that you like identify the potential pain points and then like go for those. Once I have like the list of things that I think can go wrong very easily, then I just go deep into the code, see if they do these things well. And well, sometimes they do, sometimes they don't. And when they don't, like you can write up your bug report. What's really nice about this approach is that it kind of leverages the fact that as a bug bounty hunter, you do not need to write an audit report that has to be complete. Like as an auditor, you want to make sure like you find all the bugs, not necessarily all the bugs, but you need to find, give a comprehensive report that will allow the project team to build like a really good and secure code base. As a bounty hunter, you just want to find one bug. That's your goal, or like one critical bug, I guess. And because we have this, we don't have the limitation of having to find comprehensive bugs, we can focus on just those parts of the code base where we think there will be bugs. And over time, you'll get a kind of spidey sense of what these parts of the code base are going to be like, and you're going to be like browsing through a code base and be like, this looks fishy. Let's have a look at this. I think this works really well. So I already mentioned reading documentation is kind of the first part of this go deep approach. I think reading documentation is sort of an underrated, not that much talked about approach. There is a lot of bugs, design bugs that happen that you can find by just reading the documentation. Some ideas just fundamentally don't work or fundamentally have some flaws that people need to worry about. So you can find these mistakes or critical points by just reading the documentation and then seeing if they actually implemented the necessary safeguards. So this is actually a relatively fast way of approaching a project. Yeah. And then finally, there's a toolbox mental model. And I really like this one. So a lot of critical bugs aren't critical bugs necessarily. So if you have a report on Immunify, for example, a bounty report, what's very important is the impact of your report. And to get a critical impact, to drain all the funds, it's very often the case that it's not a single bug that leads you there. It's often like a series of bugs that will allow you to get around various safeguards and measures to actually end up in a situation where you can take out all the funds. So we commonly call this a kill chain. And what I tend to do when I review a code base is I mentally, or actually write them down sometimes, keep track of these tricks and gadgets that I found in a code base. And the name gadgets is kind of stolen from binary exploitation. But the idea is that if you find I would almost say it's a low severity vulnerability. If you find a way to make the system do something odd or weird, like maybe you're able to get a system to go like right up to a certain margin requirement that is not expected, but also not a vulnerability. That might be a useful thing to set up a kill chain. So when you're reading through a code base and you find ways to do like weird stuff that's not necessarily a vulnerability, just write them down or keep track of them so that when you find an actual bug, you can have a look at all these gadgets, tricks that you found, and see if you can chain them together to end up in a situation where you can actually exploit the vulnerability and get some decent impact. All right. Those were my tips. That's, yeah. There you go.
All right, hey everyone, I'm Nat. So just to give a little bit more or context as to my background, I mainly did a lot of code review and invariant development. And so a lot of these guides are going to be kind of somewhat code review related, somewhat invariant related, and some tooling related. So to start off with, I think the first thing that at least I encounter when I look at code bases is like kind of reading through code and then realizing that certain pieces of code are much more complicated than others. And those, I think, better than ever, usually there's a bug or some unexpected behavior in those parts of the code. So I kind of separated the tips into a few different sections. I'll start with kind of tips on reviewing kind of complicated code, how to break it down into something that you can better understand, and then to kind of form that into something you can better kind of Englishicize with expected behavior, and then a brief talk about tooling without getting into specifics. So I think one underrated tip that I have is to take complicated code and then write pseudocode based on what you're seeing. So as an example, if you have, for example, a calculate and distribute rewards function, you can fairly easily break it down into, for example, part one, it calculates some amount of like how much should be distributed to certain users, and then you can then split it up into the actual distribution, so the actual transfer functionality. And then obviously after that, it has to change certain values. The benefit of this kind of practice is it takes you out of the code base and takes you into more of a high-level review of what a certain function is doing. Because a lot of the time, the function name is not actually going to match what the function does. Or it's going to match maybe a little subset or a very specific behavior of how developers expect users to interact with their system, but not the entire scope of how a user would actually interact with that function. So at least for me, when I pseudocode things out, I'm not focusing on whether, like, for example, the user rewards is the correct amount or like whether there's a rounding issue. It's more of a high-level understanding of like, what does this function do? And once you understand that, then you can go deeper down into actually like analyzing arithmetic, or in this particular case would be arithmetic, but could be really whatever that function focuses on. My next tip is to play around with the unit tests, unless you have none. A lot of times, the first thing I will do, at least when I clone a repo, is to run the unit tests and see what the output looks like. Ideally, as Hiccup said, run the coverage, but sometimes that's not actually possible. but it does tell you a story about what the developer was thinking when they were building this function. If you go back to like even just the calculate and distribute rewards, if there's a unit test based on that function, then you know at the very least, hopefully, how the developer intended to use the system and how essentially the developer forms arguments, forms like the function calls, and like what the expected behavior is. It can give you an idea. It might not tell you exactly what it does, but it will help guide your understanding of what is expected. You can play around with these unit tests in ways that I think that allow you to manipulate the code and play around with, like, say, changing an argument or invoking a functional revert. For example, if you're looking at the client code, you're looking at the unit test, and there's no test for like the reverting case, I think it's actually at least insightful to kind of manipulate that unit test to invoke certain functions or certain paths so that you understand, like if you have, for example, nested if statements, that you understand what is required to actually hit those statements. The benefit of that is a lot of the time developers are also going to go in with the assumption that users are only going to use this function in this specific way. Therefore, this if statement is only executed under these conditions. And with a unit test, you can very easily be able to test that in live time. And when you actually get to code review or like in the future, if you do get to invariant development stuff, it also means you have a better understanding of how that function works and how to get a proof of concept up if you need to. I'll emphasize while you're doing this, and maybe this ties into one of my later tips as well, is to document everything you notice about the system. So I think whenever you look at a code base, it's going to be really clear that the developer made some kind of assumption while writing this function on how it's called or how it's executed, and making sure that you write down everything you notice about the function is useful later down the line for invariance as well as reviewing the system. The next tip is realizing that how developers want users to use their system is not equivalent to how users are actually going to use it. There's been a lot of times where developers have assumed that users are always going to use their front end or a certain back end to interact with a smart contract, or that users are always going to use this very specific periphery to interact with one. That's a dangerous assumption just because the nature of smart contracts, unless you have that access control check on your smart contract to make sure that only certain users or certain users have to interact with your contracts in a certain way. If there's any kind of differential between those two expectations, that's a bug in the system, and usually a fairly high severity one. All right, so these tips, I think, help you understand what code is expected to do, but that doesn't necessarily go into actually finding invariants. So my next few tips will be based on finding invariants. To take a step back, an invariant is basically something that you expect in your system to hold true. So that can be something that's based on like a function. If you call a function, you expect something, some behavior to happen afterwards, or it can be based on the entire system as a whole. Usually the system invariants are going to rely on system behavior, system state, generally with data structures, but this particular tip is based on functions themselves. So if you're looking at a function, you can essentially, using kind of the practice with like playing around with unit tests, you can eventually determine what are the conditions required in order for a function to succeed. What are the conditions required for a function to fail? And if you just start even just creating a list of all of those cases, you have at least started to create a list of invariants that you can later check on the code base. This is important because, again, it's really easy to look at code and get stuck in the details, get stuck in like certain flows. But this practice will help you kind of step away from the depths of the code and be able to compare like behaviors of different functions. This next tip is around expected behavior of the system in terms of more of a higher level. This is related to like state changes, what is expected to change within like different functions. So for example, I think the most colloquial example is the deposit withdraw should be kind of opposite functions. Whatever the deposit does and whatever the state variables a deposit function changes, the withdrawal should essentially reverse those. You're looking for any kind of behavior that you can kind of be able to link in terms of patterns. If one does one thing, the other one should be doing something else. These invariants also, or this practice at least, also helps you get out of kind of very specific like nitty-gritty in the code. All right, so yeah, you have a list of invariants. I think the invariants help, but they're not actually useful unless you do something with them. Now, the first thing I hear is, but I don't actually know how to use a certain tool. I don't know how to use Foundry. I don't know how to use Medusa or whatever the tool is. And I'll preface this with you don't need to for this talk, because I'm trying to keep it as high level as possible so that you can use these invariants during your code review, during your whatever practice you're doing, and be able to use these invariants in a way that will help and guide the process of your code review. So generally, when I go through the practice of actually finding the invariants, what will happen is I just have a list of, say, like 50, 55 invariants that I'm not 100% sure on and any of them, but very likely every time I look at the code base and every time I look at the code, I understand a little bit more and therefore can refine the invariants to be even more specific or to highlight assumptions that maybe weren't visible before. I'll emphasize document everything you're not sure about, because in the future, depending on how long your code review is, of course, but in the future, if you're kind of at a loss and you've looked at the code base for a long time, you're not entirely sure what to do anymore, these invariants can help as guidelines for future things to explore, just because it's something that you've maybe identified as unexpected behavior, and then therefore you can continue to trace down those paths at the end. And I'll preface this with, you don't necessarily need a fuzzer or like a unit test to verify these invariants. I think it's more important that you review the code base with these invariants in mind, because then you can, for example, if you're looking at relationships or assumptions between functions, you have a better idea of what to look for, what does unexpected behavior look like, and where the potential bugs are. So with that, essentially never trust users. Users' input, always have the smart contract verify them. That's where a lot of the invariants are based in and are related. This is kind of echoing some of the previous tips on tooling. And I will emphasize that, yeah, tooling is really hard to use sometimes. I think it takes a lot of time to understand what would you use your tool for what. But I think the more time you spend using the tools, the more you understand, the quicker it is every time you use these tools to spin up like a test. For example, if your background is in, if you know how to use like unit tests in a way that's very quick for you, I think there's always been kind of a discussion between fuzzer versus fuzzer, like tester or framework versus framework, and I don't think that's a productive discussion. I think it's more about playing around with the different tools, play around with what works for you, and identifying how you want to use the tools. So related to tooling, each tool, I think, was created with a slightly different purpose. Some tool might have been created to get invariant testing up fairly easily. Some tools maybe were created in order to test and find very complex issues. And at the end of the day, every tool has its limits, but every tool has its pros and cons. And taking the time to actually understand what do you know about each tool and how you can use these tools during your code review is important. For example, if you take one of those previous invariants that you found and then you write like a unit test on it, yeah, sure, that might not be fully, that might not prove like a lack of a bug as much as a fuzzer or like a verifier or prover might, but at least you're using the tools to your advantage more than you would as a manual reviewer. You're at the very least increasing the scope of what you're learning and what you're providing to users and developers for your code base. And once you actually get to finding bugs, finding unit test failures, finding fuzzing failures, I will emphasize that any failure that you get from any tool that you're using is a potential bug and treat it as one. Because the bug, technically speaking, could be in the client code, could be in your unit test, could be in your fuzzing code, could be in your mock code, could be at any stack. And if you're just changing your code just to make a test pass, you don't actually know where the bug was, and therefore your test might actually be masking a bug. In that, I think there's kind of an endless discussion to be had on kind of the rabbit hole of reversing like why a certain test failed. And I think taking the time to really understand every layer of the code, so the unit test, whatever test that you're writing, and the client code is important because from there there have been a lot of cases in which fuzzer found a bug, unit test said it wasn't a bug, it didn't actually fail, but the fuzzer did, and it was because the unit test and the client code was incorrect. And so realize that there could be also multiple bugs in all of the different tech stacks, and realize that your fuzzing test or unit test could also be buggy. I think that's probably the biggest lesson I've learned while writing these invariants is realizing that, or another potential case is you wrote the invariant, you wrote it like week 1, and then week 3, you're coming back to edit one of your invariants and you're realizing that that's completely incorrect. That's, I think, a very common issue with any kind of testing, but especially for code bases that change so quickly. I think the more time and the more stringent we are with testing and testing practices, I think the more that these tools can help us find these bugs and essentially make us more well-rounded security researchers. So that's all the tips from me. I'll pass it off to Rajiv.
Thank you, Nat. So hopefully we have not reached a tipping point with all these tips on finding bugs. Those were hopefully some really good tips from the trenches, right? So as you've heard their introductions, they've been doing this for a long, long time. So all these have been sort of distilled. These may seem very simple and obvious, but we believe that's what it really is, right? So with my tips, I would like to take us sort of zoom out. So going from the trenches, really going to, let's say, the troposphere, if you will, right? And sort of re-examine some of the concepts that have been discussed, right, as tips. So the first thing that I always like to talk about is everything in security boils down to this, right? So for those who have done security theory, it's you can think of it as an access control matrix. So it's really all about the assets. Without assets, there's really nothing to do or steal or hack. And obviously, if you have assets, we need actors to act upon the assets, to deposit them, to withdraw them, to do anything else with them. And all these are actions, right? So the first thing in security is really about assessing assets. What are the assets? Who are the actors? And what are the actions manipulating those? So in this meme, you see that Billy, right? Billy's parent, I don't know who that person is, but they want Billy to learn about money and the importance of smart contract security. But of course, Billy is too anxious, runs off to what looks like a vending machine that really has all the assets, right? So the actors here are Billy, presumably the person handing the bill itself, and there are various actions here. You just see them sort of depositing money and maybe getting the assets. But this sort of sums up in my head what we are trying to do with smart contract security, right? So you have assets, all the things we talked about. So the first thing that we should really aim to do, I mean, here we are talking about smart contract security, but in general in security is, what are the assets? Where are the assets? In our case, it could be a simple ETH, it could be various tokens, any representations of those. And then the next question is, okay, who are the actors? And actors in the case of the blockchain systems, right? I mean, remember, we are dealing with a Byzantine failure model, right? So it's not just the users who are the actors, it's the developers themselves, right? We've all heard of rug pulls, scams, so they are actors as well. You have governance, for example, all the token holders who may decide to upgrade contracts and change a whole bunch of things within your system, they are actors as well, right? So there are various categories of these assets that we need to sort of understand when we look at a system. And of course, finally, the actions. What is happening? When is it happening? Right? The sequence matters. How is it happening? What are the various conditions under which it's happening? And ultimately, why is it happening? Right? So just because an action is allowed doesn't mean it should be allowed. So all these are sort of fundamental questions. They seem very simple, but ultimately, this is what it boils down to. So we first assess all these things, and then, of course, look at what the behavior is. So some of my colleagues talked about sort of expecting the unexpected, and this is the reality. Yeah, I don't think you can see this laser, but our expectation may be totally different from what the reality is. And this is, I think, way more real in the Web3 world than it's been in earlier with Web2 and others, right? So if you sort of dial back and look back at the history of information security, there's really two categories. There's something known as historically as misuse detection, and there's something known as anomaly detection. So misuse detection, for all the antivirus, 20, 30 years of research, you know what the signatures are of all the bad things, which is good, but then you can never really keep up because attackers keep innovating. And anomaly detection is where you really build a model of what is allowed by your system, and then you detect what the anomalies are, right? And anomaly is anything that falls outside this model of what we think should happen. So categorizing this sort of the normally and the anomaly is important at a high level when you look at a system, specifically a smart contract system, a protocol. Now notice that all anomalies need not be bugs, right? It may just be our failure of capturing what a normal model is, and this capturing may be in the spec, in the invariance, in the documentation, in just our understanding of what the system is. But it's really a small subset of these anomalies that end up as bugs. And we call this bugs because it's sort of convenient. I mean, Security purists really find it annoying because but the bugs are really meant to be annoying. They're never really meant to sort of cause real harm. So even these bugs, which are a subset of anomalies, may not really be vulnerabilities, right? And this, like Yoran mentioned in bug bounties, some of these may be denial of service and temporarily, so it may not even be a permanent thing. It may be a loss of funds, but those may really be fees under 5 different conditions. So those may be minor annoyances, right? But here we are really talking about, we want to cover the whole spectrum, but if you want to prioritize, you want to sort of prioritize the criticals, right? We want to prioritize the real vulnerabilities. And vulnerabilities are what really result in loss of funds, and so on. We'll talk a bit more. So expecting the unexpected. So as you see here, the users, and Nat mentioned as well, in this scenario, the users are really coming in. We don't know who the attackers are really. This is an open, permissionless system. So anyone from the outside, we really don't have a periphery, right? It could be somebody in the governance. We have seen governance attacks. It could be even the developers. We have seen rug pulls. And it could be coming outside the system as well. It could be any of the dependencies, the tool chain that may be corrupted. And there are numerous examples of these on a daily basis, right? So that is really what we are up against. And finding bugs, finding vulnerabilities in each and every one of this is really what we're up against. So it's really a tricky, very hard problem. So the first thing, like Nat and others mentioned as well, is assumptions. Assumptions are the mother, the root of all bugs, right? Period. So the assumptions could be from the developers. It could be, it really starts all the way in the life cycle, right? It could really come in from the design of the protocol. There could be some fundamental things that cannot be inherently solved on a blockchain, so it could stem from there. It could be in the specification. It could be in the implementation. It could be in the testing. It could be even amongst us. When we look for bugs, right, we are making certain assumptions, and those assumptions may be incorrect and actually may lead us to miss out on certain bugs. So question everything, right? This is easier said than done. And it obviously depends on the context. So if you're doing, let's say in this case, bug bounties, right? You can question everything, but you may not actually get the answers from the protocol or from the platform itself. In the case of audit contests, it used to be the case that the developers are on the same Discord or whatever channel or whatever platform you're on. So you could ping them, but then we hit a scaling problem. When some of us started out, there were like 10 of us actually competing in a contest. So it was not a problem back then, but today, it's a good problem to have. We have thousands of security researchers, including many of you in this room, who are on these contest platforms. So if you question everything, and we want sort of authoritative answers from the developers, it is not scaling, right? So do question everything, try to resolve them to the best of your ability, and see where it goes. Where do you start off? Again, basic questions, right? Who? The actors. What are they trying to do? Why are they trying to do this? Can a certain sequence be allowed? Can a certain set of conditions happen? When are these conditions valid? When are they invalid, right? And where? It could be a certain set of tokens. It could be a certain set of conditions. It could be a certain set of actors or functions. All these things are fair game to question. So that is really the mentality to go with when you start looking at a system to find bugs. And the goal, obviously, is to discover misuse scenarios, right? So use is sort of well understood, relatively speaking. You look at a protocol, you look at a code base, you see certain flows, you see the deposits and the withdrawals and everything in between, so you understand the uses. As security researchers, our goal is, one, to understand how things can be used, and really the end goal is to understand how these can be misused, right? And again here, misuse may be okay, it may be outside the realm of what is considered acceptable usage, but not everything that can be misused is really abused. And by abuse here, we mean things that lead to a tangible loss, lock, anything like that. So these become critical, again, depending on where you are. So if you're looking at bug bounties, a misuse situation may not be really very interesting for the protocol, but if it can be abused in certain ways, in certain conditions, maybe ideally you don't require any other condition for this to be abused, then that is something that's really, really bad, right? So really what we are trying to do here is we are trying to map out the attack surface, right? That's really what it is. I mean, all these bugs that we are trying to find are really entry points into the system for the attackers to abuse. So that's really what we're trying to do. Great. So now let's say we have done all this. We have questioned everything. We have made no assumptions. We found bugs. We found that they can be abused. The next big question, which is becoming a hotter topic these days, is how do you objectively, and I don't think we are at a point where we can quantitatively do this yet, but it's all very qualitative, but how do you evaluate the severity of a bug? So this is something that's been evolving in the last few years as well. For those of you who have done this, you should be very familiar with the severity matrix, right? So you have impact, you have high, medium, low, then you have the likelihood, high, medium, low. High becomes a critical, you know what the other boxes are. So severity is really impact times likelihood, right? Now what's impact? I think of the two, impact is really how it hurts or where it hurts the protocol. Impact, I think, is more objective, right? Because you can really specify what is happening to the funds, what is happening to the protocol. Are the funds being lost? Are they being locked? Is it a temporary thing? Is it a permanent thing? Is it happening to all the assets, or is it happening to a few of the assets? So all these can be relatively specified in a sort of objective manner, right? It's hard to sort of disagree on this. So that's critical to sort of focus on, the impact. Where it gets tricky is the likelihood, right? So for all the bug bounty hunters here, for all the people participating in contests, I mean, this is a very touchy point, right? Obviously, as researchers, you want to be fair and you want to sort of be as objective as possible, but this is a two-sided marketplace, right? So from the protocol perspective or from the platform perspective, they also want to sort of pay out only for bugs that matter, right? So that's where I think likelihood comes in. Is this, so some of the metrics for likelihood, is this always the case? I mean, is this impact going to happen all the time, or does it happen only some of the times? That's critical. Is it conditional or is it unconditional? So this is, I think, fairly obvious, but I think where it gets trickier is when you start looking at the conditions, right? It's really how many ifs or buts there are for this impact to happen. And the more the number of ifs and the lower the probability of each of those predicates, the lower the likelihood. So this is something that we see on a daily basis. This is not as much, typically not as much of an issue when you do collaborative reviews, because there the project has really already paid. There is no sort of conditional pots or bounties at stake. The payment, the whole pot has been paid to the platform or to the researchers, and the project typically is more forthcoming, or I should say, does not matter as much to them if it is a medium or a low. But even there, the better the accuracy, the higher the accuracy on our part, the better, right? Because think about it, the project goes out, let's say they want to make this, it matters more for collaborative reviews and protocols where they want to make the report public, right? A protocol, would you have more confidence in a protocol that has 10 criticals or that has 0 criticals? 20 highs or 5 highs? Gets trickier. 5 highs or 50 mediums, right? So it's all, today there's a mental math that happens in our heads. I mean, this is just the security researchers thinking, right? We believe, well, we think that a majority of the users don't even look at these audit reports or really understand what to make of it, right? But we may get there soon. So this, I think, is something that we need to think about. And as a collective, as a community, we need to do a better job of sort of making this more objective over time. All right. So maybe there are some Star Wars fans here, but consistencies, right? Or the lack of. I think that is where a lot of the security issues lie. Inconsistent checks. I mean, this is something that all of us who have been doing this for a while, you look at a piece of code, you see that, okay, you may not know the documentation or what it's supposed to do, but just by looking at inconsistencies, you realize that either there's something wrong, right? I mean, this is the differential stuff that Nat was mentioning as well. You see that there's something wrong, or that the the path where the check was missing was maybe an exceptional path where you don't really need that check, right? And this inconsistency is really the root of many or most of the security issues. If you map the whole protocol as a finite state automaton, a state transition diagram, right? You have states and then you have transitions, inconsistent transitions, right? On certain conditions, there is a transition that happens from state A to state B. You would expect that it happens for very similar actions in any possible flow, but then in some particular flow, that transition is not happening. And that may be, very simply, it could be withdrawal, it could be fees, it could be anything, right? There's something that's missing. So those inconsistent transitions leads to inconsistent state, which effectively is an issue, right? Depending on what that state is. If it is really the balance, then we are really in a bad position. So again, like I said, I mean, these are very high-level ones. I mean, this is where we should sort of be zooming out and thinking in terms of the protocol, right? Inconsistencies. It could not be, maybe they're not very apparent on day 0 when you look at it, but as you start looking at it over and over again, that's where you see those patterns emerging. Okay, so this is a popular meme in the Web 2 space, right? This, the image that you see, and that's typically in the context of open source and dependencies, where there is, I don't think this works, but you see the bug over there. So that's, in the case of Web 2, the dependency thing, that's not really a bug, but that is like a small, tiny piece of dependency that nobody even knows about, right? Where we are operating on the top. And if that thing breaks, the whole, thing falls apart, right? So that's the meme. So I just sort of adopted that from the Web 2 space. But I think in Web 3, this becomes even more critical because Web 3 is not something sort of different from Web 2. It's sitting on top of Web 2. And I think there are multiple things Tincho talked about. There is a workshop happening, I think, that's going to talk about this. There is a panel on this day after that I'll be moderating, so do attend. But if this is what Web 2 is, right? Web 3, we have a much, much challenging task today, right? I think the maturity of the ecosystem is much better today than it was, let's say, 8 years ago. And here I'm talking purely of smart contracts, right? Web 3, not layer 1, not layer 2, is just your dApps, all the protocols that we build and review. There are bugs in every part of the system. There are bugs in the protocol. There are bugs in the dependencies. There are bugs in the governance processes, right? And we've been slowly sort of making our way and fixing as many as we can. The point here is, as reviewers, to find bugs, every line matters, right? Every single line. It couldn't, the amount of dollars that are at stake per line couldn't be higher anywhere else, right? So if, for those of you who are coming from a Web 2 background, sure, sensitive data loss, breaches, and so on, right? RCEs, all that. But in Web 3, the loss is tangible, it's immediate, and usually it is irrecoverable, right? There's no going back in most cases. So every line matters. So when we review to find bugs, this is something we need to keep in mind. And as reviewers, when we look at stuff, right, it may not be obvious in the first pass. We may not sort of figure out, okay, what is this line doing, or maybe what is even this function doing. It's okay to sort of proceed with gaps in the understanding. But like my colleague said, make a note, come back, because every line is supposed to mean something. And if it does not, it better not be there, because it's a source of bugs. If it is not a feature, it's a bug, right? Read between the lines as well. Like Hiccup mentioned, what is there? I mean, this is I think, probably the biggest blind spot that researchers sort of fall into, because we are good at analyzing what is there. But what is between the lines is not there, so we don't think about it, right? So that is where we need to shift left, think about not just the code that we see, but about what is this function supposed to do? What is this protocol supposed to do? What is this flow supposed to do? And what is supposed to be between these two lines that is missing from a security perspective? That, I think, is critical. Our tasks as security researchers is not easy. Read every line, read between the lines, and hell, read beyond the lines as well, right? What does that mean? That's, again, going back as an example, looking at the dependencies. Things may look okay, right? But there is a dependency on an Oracle, right? Or a certain API that may be buggy, that may be faulty, that may not be within the scope of this particular review, right? Because we are sort of looking at only one part. And I think Hiccup gave an example from Uniswap v4, but it's very common, right? read beyond the lines. And that's true for us, that's true for the protocols, that's true for everyone. Oops. For any of the Matrix fans here, just like the Matrix, bugs are everywhere, all around us, even in this room. Just to sum up, look at what's there, look at what's missing. Think as an attacker, and this is something that is tricky for us to do, right? Especially maybe for people who come in with a developer mindset, because there it's all about how is this going to be used as opposed to how will this be abused. So that attacker mindset is critical. And it goes without saying, but act like a white hat, right? And this is something that SEAL 911, there's a white hat harbor and multiple things. So look at that. I think there are going to be talks tomorrow. Do attend. So things are getting better for white hats to actually act like a white hat, right, if they're one. So in terms of reporting the bugs, in terms of claiming the bounty, in terms of not being sort of scared of potential lawsuits, and they're on. Okay, and this, I think Nat talked a lot about invariance. So this is, again, what a lot of security boils down to. What are these properties, right? What properties is this protocol, is this code, is this function supposed to hold? The good thing is read the comments, right? Read the code first, obviously. Read the comments, if there are any. Read the docs, read the documentation. While things have gotten better in the last 8 years, I would say, there's still so much more that can be done in terms, for the protocols, if there are any developers here, so much more that can go into the documentation, right? That will make the protocol safer, the lives of the reviewers safer, make this ecosystem much, much safer, right? Docs can get better. Specifications, even better, right? We have several formal verification projects, Certora, multiple other ones coming up, that allow the developers and maybe even the researchers to specify what the invariants are. Of course, you can have bugs in the specifications itself, but at least it is a great place to start, right? So those can be the places where invariants can already be specified. So that's where we can read as researchers. But depending on the context, right, ask. I think one thing that is missing, that is not as good as it can be in this space, is the communications between the researchers and the developers. So time-boxed audits, time-boxed reviews, again, depends on if it is a bug bounty, how much communications can happen depend on the context. Is it a bug bounty? Is it a contest? Is it a collaborative review? Bug bounties, maybe not as much as Yoran said, right? I mean, it can be, oh yeah, no, this is a feature. No, we won't pay. Oh yes, the good news can be that, hey, yes, confirmed, right? Or looking at it more. I don't know what the labels are. So that's bug bounties. Contests, developers of the protocols are typically available, and even the platform where the contest is hosted can have people answering questions about some of these properties. This is where collaborative reviews stand out, right? Because there you're really collaborating not just with some of your other researchers, but you're collaborating with the protocol itself. The developers themselves are on the same shared channel, Discord, Telegram, whatever, where you can ask them, hey, is this a property? Is this missing? Is that missing, right? Instead of not communicating and going away into the weeds, writing an entire POC for 2 days, coming back, submitting with evidence, only to say that, oh, sorry, that's actually a feature, right? So that's wasted effort, and we can't afford to waste a single second in this space, right? So ask. Ask others, ask the protocol, ask other SRs, ask yourself, but do ask. The final one is what is actually become a separate field, a subject within the software engineering community for the last 10, 20 years, actually. It's about inferring invariance, right? So there are actually some very cool techniques where you can look at the code, apply various techniques, right? It could be machine learning, data mining. It could be different ways of inferring what the invariants are. And as a very simple example, if there is, going back to Web 2, so if there are mallocs and frees, right, where you assign memory and where you delete memory, if there are 10 paths where malloc is being done, where you allocate memory, and if there is one path, if there are nine of those paths have a free, but there is one path where that free is missing, that is a memory leak, unless that happens to be an exceptional path, triggering an exception, right? So this is sort of an easy invariant to know because this happens at an OS level or at a library level in your system programs, but up-level it, right? If you have APIs where you have similar things, foo followed by foo bar on many paths, on all the paths except a few, that is a mess, potentially a mess, right? If there are a few paths where you only have foo, but you don't have foo bar, a call to foo bar after that. So that's a very simplistic example from a call graph perspective, but that is really what inference is about, and this could apply to state, apply to data as well, not just function calls. So look at clues in the code, right? Especially when we do not have an opportunity or we've exhausted all the asking opportunities. So this is where we can look at it and sort of infer. And these are also clues that you can look at in the unit tests, like Nat mentioned. That is really where all the security clues are, right? All the paths that were tested, all the happy cases, the not happy cases, all those are really laid out. Look at them, don't get biased by them, right? Okay. Last, the 40th tip is there is no bug-free code, right? Bugs will exist as long as code exists. Just read the code and find the bugs, right? Oversimplifying it, but that's ultimately what it boils down to. There can be 42 tips, there can be 420 tips, there can be hundreds of tools and techniques, but ultimately it's really about finding what works for you in terms of reading the code. As an example, you see a lot of this in this space, right? Where people who are just joining the space want the next greatest roadmap, the shortest path to success, to their $1 million bounty or whatever it is. But ultimately, it's a lot of preparation, right? I can speak for myself and maybe the four of us here. We've been doing this a very long time. And I'm not the smartest guy, so many of you are much smarter. So you can do this faster, but preparation is key. Practice is key. But the biggest one is patience, right? Have patience with the code, have patience with yourself, see what works best for you. That's it. So I do have the privilege of quickly summarizing all the tips, the 40 tips. So 41 and 42 are really sound bites, if you will, right, of all the 40 tips. The first thing is read the code. Think of assets, actors, actions. Think of use and abuse. Challenge every assumption made in the program. Test. When it comes to testing, properties and invariants are key. Depth and breadth, Yoran talked about it. You can go deep, you can go broad, figure out what really works best. And there is no magic bullet here, right? You have to do both, again, depending on the context. Specialization and generalization, See again what works best for you. Audits, contests, and bug bounties have different, sort of require different skill sets, if you will. Ultimately, they all require, the basic security thing. But when it comes to sort of maximizing the outcome, right, it really requires a different mindset. And especially these days with contests and audits, things are also getting interesting. They're getting very specialized in terms of with all the conditional pots and the different sort of combinations of all three, right? You have contests that look like bug bounties that are sometimes thought of as audits or reviews. Scoping is critical. Scope out, ultimately it's the attack surface, but the scope that is there for you, for the review, that's critical. And then once you know that, how do you sort of pace it, right? Do you go fast? Is it a sprint? Is it a marathon? Do you want to run slow, run fast? That's a tricky thing to look at. Zooming in and out. I mean, this is sort of one of my favorites. We sort of get into this tunnel vision, like Hiccup mentioned, where you zoom in and you're focusing on this, but then it's only when you zoom out that you see that, wow, this wasn't a bug, but in the context of these two calls, there is a problem, right? So zooming in and out, and this is not sort of, there's no zoom in and then zoom out. It's not sort of a streamlined, structured process. Typically what works best for me personally is sort of doing this on a, I guess it just happens automatically. You zoom in and then look at the broader context and see what works. We talked a lot about documentation, but with the lack of that, or if it is not enough, there is also something about the gut feeling, right? Over time, you really get a sense for, your intuition tells you that something is missing here or something is wrong. Hiccup talked about the start and the end of life cycles, critical, follow the whole path. Usually it happens multiple times, some flow, something is missing, something didn't start well. With code, mock less, fork more, mess around more. Depends on your personality. Some people like to do a lot of that. Some people prefer doing just looking at the code and just keep everything in the working memory of the mental state. Frameworks and extensions, explore, see what works best for you. A lot of the assumptions are really around preconditions and postconditions for functions or for statements. Keep thinking about that. We talked a lot about coverage in terms of, let's say, your bug bounty or in terms of the scope, but there's also leverage, right? And this maybe matters more in contests and bug bounties. Leverage your strengths. Yoran talked about sort of leveraging, let's say if you're really good at L2 or you're really good at certain aspects of DeFi liquidations. There are bugs that have been found where people have found something reported in one protocol and they've gone and really leveraged that across multiple protocols. There could be forks or similar ones. Zoom in and zoom out. The other way of saying that is really dive in, right? And sort of step out, take a break, take walks, take any other breaks, whatever suits you, right? Pomodoro of your choice. Do that. And I really love this about, I think, Nat, I forget who mentioned, but the year should be underlined. It does not matter what the 4 of us say or the 400 of us say, but it's really about finding your tools, finding your techniques, what works best for you. Just because it works for one does not mean it has to work for anyone else. Prepare, practice, and patience. That's the key. And finally, it's really about taking, as TLC is just an acronym in some parts of the world for tender love care. Take care of the code, which is why we are all here. More importantly, take care of yourself. So those were all the tips. And with that, we, I think, have maybe a few more minutes for AUAs. So this has been sort of a one-way monologue, right, or quadrilogue. But yeah, any questions? I think there should be a microphone. Feel free to ask us. We should have a few more minutes, and after that, we will announce the quiz. So do take a note of the quiz as well. There are some interesting rewards for that, so yeah.
No questions.
There's one there, a couple there as well.
Testing. Hi, my name is John. Quick question is that I'm new to security and wish to pick it up. So is there any resource that can get people started?
Okay, just to repeat, so you're new and you're looking for resources. I think the fact that you have come to DSS 101 is a fantastic resource.
Yep.
There is, as of today, I don't think there's any dearth of resources online. So, right, so look it up. I will maybe shill Securium as one starting point. So do look it up. It's sort of evolved, but there is, I would say, Cyphrin, I think, is a fantastic.
Cyphrin audits.
Cyphrin audits.
Patrick Collins has a good YouTube course.
Yeah.
He covers the basics and he goes into the EVM as well. And I think other languages like Cairo. So really good, like 12-hour courses and longer. Rare Skills is another one. By the way, Rare Skills is having a Rare Skills Day on Sunday. So if you're available, I think it's going to be a fun time.
Thank you.
Yeah, so Cyphrin, Rare Skills, and there are numerous roadmaps and blog posts and articles online.
Hey, it's Sam here. Oh, that's loud. Hey, it's Sam here. Sorry to wake everybody up. But I was curious, as folks who have been in the space for a while now, how do you decide between going really deep into a specific vertical versus exploring some of the more kind of adventurous sides of development right now? I know fully homomorphic encryption kind of based chains, Starknet. So each of you, like, how do you do the trade-off between chasing something new and becoming an expert there versus just kind of going deeper and deeper into something you already know?
Personally, I just play around with everything and see what's the most fun and see what I think just in terms of like the knowledge that I already have lines up the most. I think there's definitely something to be said about no shortage of different topics, different things that you can learn. So my tactic is just kind of learn a little bit about everything and see what sticks.
Yeah, I think there's a difference between like professionally and just exploring. So in terms of exploring, personally, I just go for whatever is interesting. It doesn't even need to be Web3 related. But for like more the professional side, like you're kind of bound by who's running contests, bounties, or trying to get audits. So I guess like your more common DeFi Web3 kind of things are gonna be the things you're gonna look at most.
For me, it's primarily been Ethereum smart contract security, lately focusing more on the infrastructural projects as opposed to the latest DeFi protocol or the next new shiny object. So that's been my focus. So it goes back to my coverage versus leverage, right? I mean, there is so much happening in this space that one can endlessly hop from one to the other without really, maybe getting your feet wet, but really not understanding it well enough. I mean, especially as security research, maybe for developers or for others, that is an option, but for security researchers, you really need to go deep and understand anything really better than the developers and the project itself, right? So it doesn't give us the freedom to sort of just hop from one place to another. You really have to go deep. So that's sort of a limiting factor, but that's sort of what I enjoy.
Yeah. For me, I would say I am a heavy DeFi user. So I think it's good to have the perspective of a user trying out latest DeFi protocols. And you never know when that knowledge comes into play. So to give you an example, back in DeFi summer, when not even meme coins, all the food tokens were launching, and then there's this like Master Chef, and there's a sushi swap, there's kimchi swap, and then you just start like depositing money because I'm in here for the tech and the money. Yeah. So the Master Chef contract, like you start reading the code, and then you start realizing how it works. And then you realize protocols start forking it, and they're using it in various ways, right? So then that knowledge somehow comes into play because you start auditing or you start reviewing these contracts a few years down the road. So I think it's like exploring and also understanding from a user's perspective how you can, how you are using the system, right? And that gives you, in a sense, an advantage when you're auditing them. Yeah.
Hi there. This one's specifically for Nat, but happy for others to chime in. When you're writing notes, and more around how you structure your notes, so you go through with pseudocode and, say, writing things per function, would you tend to have a specific section just for invariants or assumptions, or do you mix them amongst everything? Because it can be pretty easy to lose some of those important things amongst the mass of documentation.
Yeah, personally, I create just a separate document just for the list of invariants because, I mean, it helps to have it in code because the next time you go around through it, you might realize something different about it. But for like talking to developers and kind of syncing with developers in terms of like correctness of invariants, I definitely put that in like a Google Doc and share it with them. I think otherwise it would be a lot harder to share invariants with developers and kind of to get feedback on whether they're correct or not.
Cool. Sorry, you have a question over?
Hi, I'm Jonas. In addition to that question, how do you make sure that you have like all the invariants completed in your list? Or not only completed, but that the list of invariants is complete?
You're never going to be complete. I think there's kind of a, like you can be as complete as possible within an X amount of time, but I think given time box reviews, given just the time differential, it's going to be really hard for a security researcher to make sure the list is complete. I think as a security researcher, my goal is to essentially bootstrap developers with like, these are the invariants that I think are true of your code base. It's obviously the developer's responsibility to go in, make sure they're correct, make sure that they are accurate, and then hopefully for a developer to continue extending that list and continuing to change that as their code grows. But I can say for certain I've never been in a position where I felt like the invariants that we've considered and kind of thought up during a security review was 100% complete.
Cool. Okay.
Hi, hello.
Time for one. We have time for only one more question. So
Yeah.
Hey, this is Snow. And, you know, everyone knows AI is becoming very powerful tools, yep. Especially when we build protocol, when we coding. So my question is relative to the combination of AI and you know, blockchain. Maybe we can use AI for our daily development and the security research. Mm-hmm. So I have two questions. First is how AI can empower, you know, secure audit. What kind of tools, what kind of things you do with AI during the security product? And my second question is, what's your recommendation for those DeFi builders and protocols to use AI to empower their securities and you know, daily works? Thanks.
I can take it. Yeah, so AI, I think we've seen a good use case is for churning out report issues. So I think EVOM, for example, he uses an AI tool to help write out his report. But of course, then after that, he does a manual review and makes adjustments as needed. The other is for kind of like throwing documentation into an AI bot, and then you ask it questions and you get it to ask questions back to you. So it kind of enhances or refines your understanding of the protocol. And if you're unsure about something, just ask. Personally, I use ChatGPT. When I'm unsure of something, I'll just like ask it as and when I'm unclear of something, or it's like help me write out this issue, and then I'll make some modifications.
Yeah, I mean, just to add to that, I think there are multiple projects in the space trying to leverage AI tooling, right? In the entire life cycle. It could be for program understanding. So in terms of, feed it the code and ask questions about it. And of course, like with anything else, hallucinations are a problem, right? So you can't just rely on it. And I mean, this I believe is a big, I don't know how bad the problem is, but I believe with all the bug bounty platforms, all the AI generated issues is causing a lot of spam, right? So it's sort of the downside. But I mean, I think we're just scratching the surface in terms of how this is going to help. And yeah, I'm looking forward to see where this evolves.
Yeah, I mean, it's very promising, but unfortunately, a lot of the AI approaches have been like, hey, I put this smart contract in ChatGPT and it gave me all the issues, and then the contract is like the DAO hack. This is like the weakest form of evidence that it can work. So yeah, it's really cool, could be really cool. Right now, I think the main viable approach is to use it for code understanding, not necessarily for or LLMs in specific, not necessarily for actually discovering the vulnerabilities on its own. So more like the hybrid, like working together form. Yeah. And I guess, so one nice bit might be in invariant development. Like you can kind of work together to, like you can come up with your list of invariants and then more quickly develop them in a various frameworks. So maybe instead of Foundry invariant test, like you might improve your workflow there. One thing though, you also said like how could projects use AI? I forgot the name of the paper, but there was some research into the code written by AI and vulnerabilities introduced by the AI itself. And it turns out that there's some risk there as well, where the AI, even though you tell it to build secure code, it's not always very good at doing so. So yeah, I would be really careful with asking your ChatGPT to build a whole DeFi protocol and then just deploying it and putting your money in.
Yeah, that may lead to a whole class of sort of AI copy and paste bugs for programs that, where the training data involved buggy programs, sort of, your Copilot and other things sort of filled it up that way. Yeah. I think we are out of time.
We need to wrap it up because lunch is ready. So everyone, please, if you want to have lunch, you can go to rooms 3 and 4. It's on the right. Make sure you have a wristbands and enjoy your lunch.
Okay. And one. Mata has the volume. Okay, good. We're back.
No worries. It's fine.
Oh, we're back off. Okay. So we have this quiz. Feel free to take it. It's a very short. I mean, this is a typical Securium quiz. We call it races. That's why you see that word. It's 8 multiple choice questions. We have the most secure password. Feel free to take a photo. Go, attempt it. You have 16 minutes. Try to submit it by tomorrow. And the top 3, by scores, will hopefully win, DSS 2025 tickets. So yeah, if you want to be here next year with a free ticket, feel free to take this quiz and test it out. Thank you.
Oops. Is it? Ah, okay. All right, hello. Well, welcome to the control workshop here in DSS. So basically in this workshop, what I'm going to try to show you is sort of like the grand, like high-level picture of what you're in for when you want to use control. And sort of what I hope that you get from this talk is basically the foundation of what you are going to be dealing with when you start using control. We have killer documentation for a lot of features. So basically what I want you to get from this is just being able to go to this documentation and be actually familiar with the whole process and know what to expect. So, but first things first, who am I? I'm Juan. I'm a verification engineer at Runtime Verification, where control is from. And yeah, we're a formal methods company. We do formal methods for Ethereum, also for other chains. And yeah, you should check out our work because it's very, very nice. The way to get control, you can just run this bash command to install KApp, which is our package manager for our frameworks, and just you can use control from there. And also there's a repo with the examples that we're going to be showing in this workshop. You are not required to get the repo for this presentation, but you can recreate the examples from there. So this is where your control journey starts at this very moment, and it starts with read Jesus or Foundry. Right, so basically, if you know Foundry, that's basically what you already know how to write control proofs. Like that's because basically control proofs are 100% Foundry compatible. And so basically, you can take any Foundry test that you would fuzz over, and then you can run it as a control proof, right? And you will be executing it symbolically instead of concretely, and we'll see what that means a bit later. So the way to basically take a Foundry test and then turn it into a control proof is you swap. Instead of forge build, you just have control build, and then instead of forge test, you have control proof, right? And these two commands basically do what you would expect them to do. In Foundry, to run a test, you need to prefix it with tests. With control, we actually have two more prefixes, which is proof that come from HBN, which is another formal verification tool for Solidity, and then we also have check, which comes from Halmosh. So this means that writing control proofs, it's compatible with these other tools, or you can also take these properties written for these tools and bring them over to control. So it also has great compatibility features. Also, as you would expect with something that's a Foundry test, we also have compatibility with cheat codes. We also have our own cheat codes, so besides supporting Foundry cheat codes, we also have our own. But also recently, Foundry have included some of which were our cheat codes initially into their cheat code suite. So basically, for the compatible Foundry cheat codes, you get mostly the most execution-related cheat codes, the way that allow you to manipulate EVM state and so on. We don't have 100% of the massive amount of cheat codes that Foundry has. The ones that we don't have usually it's because we haven't see that we need to use them. So if you're missing any, feel free to reach out, and we also incorporate them based on what our users need. So yeah, feel free to just reach us out. Also, we have our own cheat codes, which are because we're doing symbolic execution rather than concrete, right? So we needed our own type of cheat codes that was, important for symbolic executions. So yeah, we added them, and one of the reasons why we initially have this, instead of having a test prefix, have a proof prefix is because if you have custom cheat codes, they won't run as a Foundry test. So you want to separate them and not to break, Foundry test suits. So with some of the cheat codes that are our own, Foundry won't run, but this is big of an asterisk because Foundry recently added some of our cheat codes. In particular, these are the new cheat codes that were control inspired. This set arbitrary storage, copy storage, mock function, and then this random uint bool address and bytes. So the control equivalence, this is not exactly the same cheat code in the sense of the naming, but what it does, it's sort of equivalent brought to the realm of fuzzing. So set arbitrary storage for us, it's symbolic storage. For copy storage and mock function is the same. And then for the random, we just call them fresh, because in the symbolic context, it's not random itself. It's just a fresh variable. So basically what set arbitrary stars does, in case you don't know, in Foundry it just sets a concrete fixed number for any uninitialized or unread slots of a given address. And for us, it sets the entire symbolic storage, the entire storage as symbolic, right? Copy storage, it does with what it says. It just copies the storage from one account to another. We also support copying transient storage when needed. And in Foundry, as a caveat, you cannot use both copy storage and set arbitrary storage. We also have this mock function, which is sort of like a mock call, but on steroids a bit. So mock call the cheat code mock call would just swap a function call with a specified return value. In this case, mock function, what it does is mocks the execution. So it will swap the call with what you can consider a model of the function that you're mocking. And so that is useful if you have a very complicated function and you want that you want to execute just sort of like a model or a summary of it, but you still want to run it, not just get a concrete return value. And then we have this random, which is just in Foundry just a new fixed value, and for us is a fresh symbolic variable. So these cheat codes are not yet implemented in Foundry. They are sort of in the pipeline. So these are cheat codes that we still have, which is sort of, for Foundry you have expect call, which is like for us expect regular call, but we wanted to also have some sort of more granularity where we're writing our tests. So in particular, we have these calls with these cheat codes, which are kind of self-explanatory. So basically, up to this point, why do we need to be so symbolic, right? Like you have Foundry, which fuzzes concretely and so on. So why is there need for symbolic reasoning? And well, a bit the reason behind this is that with concrete, like the state space is just too much big. So with symbolic reasoning, it allows you to actually explore basically the totality of it if you do it correctly, or at least a way bigger amount of the state space, and to ensure that your function has been as thoroughly explored as possible. And so, for instance, here, this could be like just a Foundry test, but what executing it symbolically allows us to do is to make sure that there is no value that's being tested. That if this passes, there's no value that will make this test fail. Whereas with concrete execution, if you're fuzzing, you will never get to this level of assurance. So what is symbolic execution in this case, right? So as we said, for concrete execution, basically you just take concrete values, you start with concrete values, then you execute, and you always get sort of a concrete result. Whereas with symbolic execution, you can think of it as executing it as if it were variables from like a math equation, right? So you start with symbolic, in this case, for instance, if you're trying to somehow verify the behavior of the transfer from function, you will start with symbolic values for your pre-state, then you will execute with some symbolic values. And what you will get is an execution branch, an execution tree, where each branch basically summarizes a lot of behaviors that can be done in like a lot of concrete tests. And in this case, you just get like, for instance, in this example, like what if in the transfer from, what is from is different from to, and what if they're equal. And then what you get is like a mathematical evaluation of this and sort of like a symbolic summary of what's the behavior of your function going to be. And so, as we said, symbolic execution, you're executing, but in a symbolic way, sort of like, just think of it like variables in a math equation. And you start from a symbolic state, and you end up with a bunch of symbolic states, each of them symbolizing where can your function end. And so, taking also one step back, it's like, so what is formal verification, right? More broadly, formal verification means like you assert properties of your code, which is called specifying it, which in the case of control, you can do it with a foundry test, with a foundry property test, and then you prove, that your code actually satisfies your specifications. There are a lot of techniques to do this, like to take some specifications, some blueprint of what your code is supposed to do, and then doing some mathematical reasoning on it to make sure that your code actually follows these blueprints. Symbolic execution is just one of them, where we execute your code, as we said, symbolic parameters. Then you get all this branching, and basically you just get like like what's your function actually doing, and then we check that for every possible path, execution path that your function can take, your specifications, your blueprint is complied with. So it's also the case that there are many techniques for doing formal methods, formal verification, and there's a spectrum, right? Like they vary in the degrees of automatization, and they also vary in the degrees of which is the problems that they are able to solve. So meaning what's the kind of statements that you can prove. And usually, as a rule of thumb, the more complex, the more automated a proof is, or rather the other way around, the less automated a prover is a tool for doing formal verification. Usually this translates into the ability of proving more complex problems. This is also like sort of like a rule of thumb, but basically there's this spectrum of the least automated you are, usually the more like general problems or the more complex problems you're able to tackle. It is also true that the more automated you are, the easier to use it is, right? And especially for the kind of problems that it's automated to solve, these tools are really fantastic for just ease of use and just to get you going. And I wanted to give you some like examples of how does these different sort of proof systems work, right? So basically you have interactive theorem proving, which is like the most automated thing that you can get, which is like mostly manual, and you also rely on constant feedback from your tool to let you know where you are, and it requires a lot of user input, and usually the learning curve is quite steep. And then you also have automated reasoning, which usually doesn't require any interaction, hence automated. And it's also usually the case that you don't have any insights into what is the proving process. So it's sort of a bit like a black box in the sense that you query it for a proof, saying, I want to prove that my function something. And then it will say yes, no, but there isn't as much insight as with the interactive tools. So for instance, here's an example of an interactive tool. It's not very important what it says, just, so this LIM4, this is what is called an interactive theorem prover. And in particular, this proof proves that, if a graph is Hamiltonian, then it's connected. We don't really care a lot about this, but the thing is that with interactive theorem provers, you can get as far as into formally verifying virtually any type of math, like not just, programs and functions, but like literal theorems about very complex things. This is what a proof looks like there. Like the statement is like the first and second line, and basically the user needs to fill every other line here, which it doesn't look very intuitive. And the type of feedback that you're being given by the machine while you run this looks like sort of like this. So you can tell that there's somehow a steep curve into learning this sort of stuff. It's also very rewarding in the sense that it allows you to go very deep and prove like, arbitrarily complex properties about math or your code, or you have it. Then we have automated proofs, in this case, just with Halmosh, and this is how an automated proof looks like, in the sense that, you just run it and it says if it passes or not. If not, it gives you a counterexample. It is also true that with automation, it means that you can get unknown results, meaning that the tool may just run out of time and saying, I tried to prove this automatically. There's some bounds of time because the tool is not going to be running forever. And if it doesn't find a solution to it, it will just say, hey, I didn't just find the solution for this. And then I want to give an example of control, because control is sort of in the middle. It's automated, but it's also interactive. So this is one example of what a control proof looks like when it passes. So it just sort of like, it looks like automated, like you just run it and it passes or not. But we also get feedback, which is one of the key principles that you need for an automated procedure, right? So in particular, with control, the type of feedback that you get is this tree that's made of all of the possible execution paths that your function can take. In particular, here we're seeing a branch where it tells you which is the path constraint that you're traversing, right? So, for instance, here it's telling us that y is different than 0, and that x dot y it's less than max u into 56, so there's no overflow in the multiplication and so on. And so basically, like, okay, I'm executing the function in this context. And what we see here are nodes. So basically, the nodes are snapshots of the execution at a given point. And in these nodes, what you get is like the full state of the OR formalization of the Ethereum virtual machine. So you get this sort of HTML-looking configuration, and here it's contained all the information of OR formalization of EVM. So basically here you have, we go like with cells, right? And so the KSL, for instance, it's our formalization of the execution of EVM. And then you have things like the schedule, which we default to Shanghai, but we also support Cancun. And changing this is just one command flag away. You also have the output. You also have caller, call data, and so on. Word stack, local memory, so basically everything that you would hope for when executing, like, okay, what's the state of my smart contract when I'm actually running this function? And then we also have the interactiveness part, right? So because here, so the way this goes usually, it's like you execute it, then you inspect a bunch of states, and then you say, okay, this is telling me that my function is behaving like this, and then you can tell control to say, okay, now I require you to reason about this in this specific way, and we do it through what we call lemmas. We'll go over this in more detail later, but this is basically what interacting with control looks like. It's writing these files that then control will parse, and then we'll reason with taking into account what we wrote. Here's also a sort of like snapshot of this is a non-exhaustive list of formal verification tools available for the Ethereum ecosystem. But yeah, we luckily in this space we are not short of tools, and there are fantastic teams working on formal verification for this. So I heavily encourage you to take a look at every tool, because as we said, there's like a spectrum of automation versus ease of use versus kind of problems that you can solve, and so there's one tool for each job, I would say, or at least for the kind of verification that you want to do. So yeah, definitely check them out. That's nice, but this is a workshop, so let's get some work done. We're going to be verifying some stuff with control. So first things first, I want to talk about hardware requirements because control is quite resource intensive, and we've had these cases in the past where it seems like control is crashing or failing, but it may be that it's because of lack of resources. So we require a minimum of 16 gigabytes of memory for things like building and so on. There's some caveats, like if you're using this Windows subsystem for Linux, I think it by default only allocates like 2 gigabytes to it. So you should look that up and make sure that you have, if your machine has it, at least give 16 gigabytes of RAM to it. And same with Docker containers. I think in Macs it's also capped like at 2 gigabytes or something. So just make sure that you have these requirements like set up. And also for running proofs in parallel. As a rule of thumb, we're like 8 gigabytes of RAM per proof. This is not like, you can experiment with it. Your computer is not going to burn or anything. But yeah, this is sort of like what we look to usually. And so this, you may feel, if you've ever tried control, you may feel a bit represented in this picture in the sense that there's a lot of options and there's a lot of things that you can tweak with it, and it can be a bit overwhelming at the beginning. So I'm hopefully trying to give you some clarity into all of this. So this is basically how the interaction loop with control looks like. So you would start right at the build stage, right? You first build, then you prove, and then you inspect, right? So you build to, well, first be able to prove, but also to include new lemmas. This is one of the reasons to keep rebuilding stuff. And then when you prove, basically you will produce what I showed before, this symbolic execution tree. And basically, there's like a subloop there in which you inspect the symbolic execution tree, and then you can manipulate. You can, you can say, okay, you did something weird here, and I want to zoom in on this. And so there's this cycle in which you prove, you produce your symbolic execution tree, which is like the summary of how your function behaves, and then you can inspect this summary that control produces for you. And just sort of gain more insights into what's happening. And then out of those insights, then you may be wanting to write more lemmas to then include them again in proving. And this will make some sense in a moment, but this is like high level how the proving interaction works with control. So yeah, if you just go and do like control build help or control proof help, you will be bombarded with all these options. And sort of, if you try to sort of understand which ones are the ones that are more useful to you, it can be a bit overwhelming. So let's start with control proof, build. And see among all of these, what is really important for you as a user. So basically, the important options revolve about including including lemmas, basically, excluding some if you want to, and also regenerating K definitions, which this is used to include new lemmas. So basically, to include auxiliary lemmas, we have this flag, auxiliary lemmas to control build. At the bottom, you can see sort of the command that you would need to put to execute this step. These auxiliary lemmas is just things that we have encountered and working with the tool, and we found very useful. So this is just also sort of, if your proof is not working from the beginning, this is something to try right away because this enhances control's ability to reason. Then you also can include your own lemmas. We do this with this, require, and then a path to your K file, and then the model that you want to require. This is not important that you memorize any of this. It's just so that you know how it looks like. Then we also have some catch-hack lemmas that are included by default in control. You can also exclude them, but they are basically working assumptions on how the catch-hack should be. Basically, we assume injectivity and we assume some collision resistance from symbolic values. These are not mathematically sound, and this is why we include them as a separate part. These are not part of our core semantics of EVM. But these are working assumptions that we need to do in order to be able to reason effectively about EVM code. And then you can also just regenerate K definitions in case you include some lemmas with regen or recompile. So this is a bit of how like the full control build command looks like. And also we have control proof. So again, control proof has even more options than control build, and so it can be really daunting to just go about it. Again, the relevant options are for proof execution tweaks. So it's just getting, zooming in into the execution trees, doing some loop exploration behavior, and also to increase the performance of control. To get, a more detailed execution trees, remember we have a node. So an execution tree is basically its paths based on branch conditions, and then we can specify when do we want to create a node, which is like a snapshot of the entire state of our EVM while executing your function. And so we have a lot of, rules to create new nodes. We have max depth, which basically means after doing X steps of execution, just make a snapshot of whatever you have. Then we can also specify when do we want it to break in terms of, for instance, AVM opcodes, either every AVM opcode, every jump I. We also have now jump. We can also, like, if you say, like, I want to know where I'm jumping to a function or when I'm jumping into a loop or whatever, you can break on jump I will allow you to create a KCAG where you have snapshotted every time you did something like that. Also on storage and on cheat codes. We also can change the loop exploration behavior. So one thing that's in control by default, we don't bound loop execution. This means that if you have like an unbounded loop, you can get an infinite a potential infinite execution tree. And the way we do it, we allow bounded loop reasoning in control via this BMC depth command, where you specify how many loop unrollings you want to get. So basically, you will enter a loop, and then you will execute it the amount of times you specify, and after that, it will just conclude the proof and give it as passing. And we can also specify loop invariants, which is sort of like the other way of tackling loops, which is instead of just unrolling a finite amount of times, you can actually specify what's the expected behavior of your loop, and then control will take that into account. And then as per control 1.0, which we released some months ago, we also have this optimized performance flag, which will just make things faster, and you don't have to take, you don't have to tweak some parameters yourself. It will just get the faster execution running. And it will also do like parallel branch exploration, which you can set the number of how many branches do you want to explore concurrently. Again, this depends, like the number of branches that you can explore concurrently will depend on the hardware that you're running this with, but yeah, just keep that in mind. Okay, so you just control proof something and it passed or failed. Now we need to inspect what control gave us back, right? So we have basically two exploration commands. One is control view KCFG, which is a terminal UI interactive viewer where you can click on the different nodes and see the different state snapshots that it took. And there's also control show, which is just plain CLI output. And also, we are introducing K as a service, which it also gives you a web view of your proof, and it's a very nice web view. And so, yeah, more on that also later. Once you've seen what your proof looks like, you can also do some manipulation, which basically means you can remove nodes. You can, say, I don't want to explore this branch anymore. We'll see some more of that later, but I just want you to get with, like, the main point I want you to go with, it's like you really can inspect everything you want about your function execution with control. Then you can, manipulate what the snapshot looks like and start reasoning from there. So maybe you're a bit like this after, all this mambo jumbo. So just remember what we're doing here, basically just these different steps where we're either including lemmas, we're proving and then producing these symbolic execution trees, and then we're manipulating them, we're expecting them, we're doing a lot of things with them. And out of all that interaction, we can write new lemmas that will make our proofs advance further. Okay, so now let's apply the verification cycle that we just shown. We're going to be working with this example, which it doesn't look very super interesting at first, but it will tackle the whole thing. And it's a very, I think it's a very complete example, as in how is the complete usage of control look like, right? So this basically is just adding numbers from 0 to n. So we start with n, then we have these two variables set to 0. Then we go into this loop that we just add 1 to I, and then add I to result, and then we return result, right? So what we expect intuitively is that sum to n of n is actually the adding numbers from 0 to n, which coincidentally this has a very nice mathematical closed formula, which is this one. We won't be showing this in the proof of this statement in the talk. There's a very nice post that Raul here recently did about formal verification on loops, and the proof is there. So I encourage you to go to our blog post page and find it. And so after looking at this, we would expect that our specification for the proof sum to n looks something like that, right? So with this in mind, we can just build it and then just try to prove it. And as I said before, control by default doesn't bound any loops, and sum to n is basically just one loop. And so what we would get if we just execute what we have here, it's something like this. So this is the execution tree, sorry, the symbolic execution tree that I was talking about earlier. So basically, you just get these nodes, which are just snapshots of what you have, and then basically here, you can see a jump I. So the thing also in control is that you're working with EVM bytecode. So even though you write your test in Solidity, what you're actually verifying is what your code is actually being compiled to. So here we see that we are entering the loop with this jump I instruction. And we also see that we're checking if n is less than 0. So basically what this is checking, even though this is not exactly the condition that we put in, but the compiled code, what it's doing is checking, should I exit the loop or should I continue and enter the loop, right? And so it's checking, is it n less or equal than 0? So should I just exit? And then control just branches, right? This is symbolic execution, so then control just says, hey, I don't know if n is less or equal to 0. N is a symbolic variable. So let's just suppose, on the one hand, let's just suppose it is. And then if it's less or equal to 0, it just exits the loop. We can see it exiting the loop here. And then it just says, OK, then I just finish. So for this branch, I do get to a successful state, and your test passes. And then it goes on and says, OK, what if actually n is greater than 0? Then we enter the loop. And then we execute a bunch more. And then we do one iteration, and we say, hey, now, what if n is less than 1? Then if that's the case, then we just exit. And if it's not the case, we're still in the loop. And then control will just do that again with 2, and with 3, and with 4, and it will just not stop. Why? Because we are not bounding loop execution here. So by default, control just will start to create this potentially infinite execution branch, right? Execution tree, sorry. Unless we at some point we stop it. But if not, as you can see, it will just get bigger and bigger and bigger. Here is where I stopped it. And so how do we go about this? Does that mean that we cannot verify this with control? Well, luckily, what we have here is that we can add some BMC depth. So we can tell control, hey, at some given depth, just accept the proof. Like, I just want to execute this symbolically, and if it has worked for the first 4 iterations, let's just assume it will work for the other, how many it could have, right? And so with that, it will pass. So I executed this proof with BMC depth 4. and we want to see how the execution tree looks in this case, which it will look basically the same as what we just saw, but at some point, again, it's branching, then we enter the loop, and then it says, oops, and then it says, yeah, sure, everything is fine. And then we will do that several times, and then, right at the bottom, exactly. And then we get here, and then it's like, well, is n greater than 4? Should I enter the loop? And then it's saying, well, here I'm assuming it is, but I would be entering the loop a 5th time. So that's out of our, that's out of our bounds. And then it just cuts it and say, okay, I give this, for every iteration that I entered, I successfully completed the test. In this case, I'm just going to end the test here because you told me so. And so that's fine. But for instance, what happens if we have, say, a malicious sum to n? And by malicious, I mean, like, what if, we are executing the loop, but it says, if I'm greater than 4, I'm just going to give you an incorrect result, right? Well, the thing, what happens here is the same, basically. You will, if we, I think I have it here. If we run this, oops. Sorry about the live demo thing. Yep. Well, you can see here, if you run it, basically it will pass. You will have the same amount of nodes, and it runs in basically the same amount of time. And so here what is happening is that the behavior that would make this proof fail, it only happens after a certain amount of iterations. And so how can we basically go about this, right? Yeah, if we execute it with this, basically we'll just succeed. So how can we solve this? Well, we can solve this with loop invariants. So loop invariants are basically their properties that are supposed to hold before the execution of a given piece of code and after the execution of a given piece of code. Invariants can also be trivial properties because something that holds before and after doesn't really need to be meaningful about your code, but you want this to be something actually meaningful about your code. So basically a loop invariant, you should craft a loop invariant in the sense that you should craft a property that captures what your loop is really doing. I will also say crafting loop invariants, it's a problem that is arbitrarily hard. Like this can be quite a challenging problem to face in the sense that, for instance, if you had a very dumb loop that it just computes, you just give it a number and it computes the nth prime number, like coming up with a loop invariant for that will basically grant you the novel equivalent in mathematics. So it's really like, it can be a very challenging endeavor, but control supports it, and there are ways to sort of automatically or pragmatically come about with loop invariants. So let's just start forging the intuition here on how does forging a loop invariant for this look like. So when we start the function, we basically have that result is equal to I, which is equal to 0, which coincidentally is also equal to the closed formula that we hope this function to be equal to. And after executing the loop, we would get that I is equal to n, and then hopefully we would get that the result is equal to n times n plus 1 divided by 2. This is what we want to actually know. Like this is our intuition, but we don't know. And so these are sort of the loop invariants recipe when you're looking at Solidity code. So you basically look at the loop head, see what you expect the state to be. Then you execute the loop, then see how the state is updated. And then you sort of want to generalize that into a property that captures, what is the state updates that your loop ends up with. This is for Solidity though. For EVM, we have to do some more extra work because we first need to identify where the loop head is. because that's not you know, super trivial to do when reading bytecode. And then we just, again, sort of inspect how the state is, see how it's updated, generalize it. It's very important with control. Once you come up with what you think is a sound loop invariant, control allows you to actually prove that your loop invariant is correct. And then basically you can include this loop invariant as extra knowledge to control to say, hey, my loop takes states that have this sort of form, and after executing this loop, it transforms it to this different state that has this particular form. And in this way, what you're doing is actually you're effectively summarizing the actual behavior of the loop, and you are sort of executing it to completion, which it gets rid of just executing a few iterations. You're actually encapsulating the entire behavior of the loop in this using this invariant approach, right? So first, we need a word about lemmas, because you need to understand how to write a bit of K, which is what control is based on, in order to feed it lemmas. And so basically, very quick, the files starts with some requires, which in here we import a formalization of how Foundry execution works and how EVM execution works. Then you just have this module, where you will have your lemmas, which are like these reasoning bits that control takes to enhance its reasoning power. You import some modules, and then basically here's like the meat of the file, which is the rules, or lemmas. So a rule basically just has the syntax: rule something, require something, and then simplification. For us, a rule is something that is a rule that has the attribute simplification, but yeah, basically just rule. Then you just write your rewrite conditions. This basically means, if you start with the left-hand side of this rewrite, in this case bool toward x, you will rewrite it to whatever is on the right-hand side. So this is the rewrite symbol. So this tells us that you start with this state, and then you will end up with this other state. Then you can have a requires clause, which basically is just apply this, this transition between two EVM states. Just apply it only if the condition that goes after the requires clauses is fulfilled. It's not necessary to have a requires clause, but it's there in case you need it. And then it's just the simplification attribute, which is sort of like a particular type of rewrite rule that we have. Great. So let's prove the invariant, but first let's see how this looks. So we want to, in this case, we want to first inspect the configuration that control has given us, right? So when this loads, we sort of go here. Just as also a note, we executed this, if you remember from way before. We had this break on jump-i instructions, which basically tells when you are doing symbolic execution and you face a jump-i, I want you to create a node, which basically a node here is just I want control to snapshot whatever the state is here for me to execute it. And we did this because since we're entering a loop, loops start with jump-i's. So basically we just scroll down. Also, sort of like a warning, sometimes you will have to aggressively scroll down or up due to the amount of information that controls gives you, but that's just something to get used to, and I think it's actually a pretty good thing. So here we are, node 27, we are at a jump-i, and here we are splitting, so here we're branching. TLDR, this is our loop head, really, as we saw. It's seeing if n is less or equal than 0, and if it's not, it will just exit the loop, and if it is, then it will just enter, right? So I executed this with BMC depth 4, and here our goal now is to see, okay, I have this jump-i here, node 4, and this is the very first time I'm entering the loop. And then if we scroll the way down, we can see, yeah, this is where it bounded. This is the last time it exited the loop. Here. This is the last time it exited the loop. And so basically what we can say now is, okay, give me so the way we're going to come up with the invariant is we're going to see which are the state changes that happen between the first time we were entering the loop, the first time we were at the loop head, and then the last time that we let control execute, the last time it exited the loop. So the way to do this is via this control show node delta. So what this will basically do is it will take two nodes and it will perform the difference of what has changed in the EVM state between this node and this node. And if you notice, we're doing it with node 54, which is the first node that's actually jumped out of the loop. So if we just do the node delta thing, it may take a little while to just load, but it will basically give us, again, the entire configuration, and then at the very bottom of it, it will give us a configuration that contains the state delta here. So it contains basically what has changed between node 27 and node 54. And we can look at it by looking at these arrows. So basically, it said, okay, what has changed is, in the K cell, which basically is where the EVM code is executed, you went from this jump I on this condition to basically just jumping. And then if we scroll a bit down, everything else stays sort of the same. And the only thing that changed as well was that in the word stack, we started with these two variables, and then we arrived to 2, and then here to 3. And this is for the second execution. So once we see this, our job is to say, okay, we've gotten these state updates. What is the general form of this, right? And basically, that's how you can craft an invariant with control. You can just come here and say, okay, we know we were here, and then we jumped here. That's concrete. And then, so first of all, what we're going to do is we're going to, first craft the thing, and then we're going to prove that what we craft is correct. So yeah, basically we're just saying, we have this state, and then we're just going from here to here, and then we generalized what we saw. We generalized what we saw here into a more abstract formula, and just saying, from I go to N, and then from this closed form we go to this other closed form. The thing is, this is a claim. So maybe this is too detailed, but what I want you to get to remember of is this is a claim. What you're doing is you're crafting a state difference, and then you're actually proving that the state difference holds. And this is done via this claim instead of a rule. We're just saying, yeah, this is how the K execution cell is going to differ, to change. There are some stuff that we want to keep just to keep the rule actually provable in the sense that this is how we executed this program. Here is the main let's say source of reasoning that you want to have. So the main abstraction that we're doing is coming from what is written here to what is written here. And that's where the challenging part of crafting loop invariants comes, which is you have to understand your code, you have to reason about the properties that it has, and then you sort of go from this concrete difference to the general form that it should have. Then we have the same PC that we were executing with, and then some more stuff, and then some well-formedness conditions. And the thing is, what we're saying now is, hey, this can be turned into a rewrite rule. So this can be turned into basically just telling control, whenever you are at this program counter, whenever you are facing the loop head, which is this thing that we have here, just rewrite it to this, and then the general behavior of my loop is going to be this transition, right? And with this claim, what you're actually doing is telling control, prove me that this is correct. So this is not giving the user like you just write whatever and then control will just take it. you're actually able to take control and say, just prove that this state transition is actually accurate and that it works. And then you just, you can translate this into a rule once you have proven it correct, which basically means just taking a bunch of other constraints and putting it in the bottom. But basically, you end up in a loop in which you actually you have this state transition, and this captures the actual behavior of the loop of the while loop that we were facing with. Once you do it, you can actually prove the statement without any BMC depth, so it will be capturing the loop behavior in full. And that's how you basically can verify a loop with control. We have used in our engagements because also so we have been dealing with a very on the face kind of loop, but also, for instance, there are some loops that are inserted by the compiler, not with the recent. With the latest one, since we have now mcopy, but it was the case for I think it was from Solidity 0.8.24 previously. If you had a bytes memory argument, you will the compiler will insert there a loop that you will need to reason about. And so, for instance, this lets you reason about it in full generality. So I hope you are excited to try control. I try to show here from going from the basic use to actually show you an advanced example of how to use control. I think we have killer documentation on this. You can also have control in your CI. So please feel free to go to the documentation, read it, and we're also very responsive and active. So if you want to get in touch with us, feel free to come to our Telegram channel, to our Discord. We're more than happy to hear from our users. And so thank you very much for attending this talk.
I didn't get the memo on getting the adapter. It looks like we need a USB-C to HDMI.
Yeah. Can you ask them to bring?
Awesome, thank you. I can just stick. Oh, yeah. I'll just use this. Yeah. Okay. Can I get my notes here? Seems like it shows that up there too, though.
Because it's just one way. You have the extend or you have the extend.
Okay.
Yeah.
Awesome. Perfect. Thank you. Okay. Hello, everyone. I am Elliot Friedman, and today we're going to be talking about secure smart contract development. I'm the founder of Solidity Labs. We're a boutique consulting firm, and we build smart contracts for our clients, and we have a very keen interest in security, and so really excited to share some of the stuff that we've been working on with you guys here today. Okay, so high level, what we're going to be talking about. First, we're going to talk about the different types of smart contract systems and the types of governance that come along with them. We're going to go over the security stack, which is the types of tools and testing methodologies, processes, and procedures that we can use to find bugs. We're also going to go over blind spots and how they emerge and how we can remedy them. And that will be around where bugs are commonly missed. And then we're going to do an exercise. So this will be interactive, where you guys will be able to pull down some code, and use some tools to find these bugs. Okay. So it's important to first start off with categorizing the different kinds of smart contract systems. So the first kind of system is immutable. So this is one that has no admin keys, no upgradability. There's very little. There's not going to be any tooling around governance because there is nothing to govern. There's no trusted third party. A good example of this would be like AMM contracts that don't have any fee switches. So you could look at the Uniswap factory contract. You could look at router contracts where different actions are bundled together. Then we have governance minimized, and so these systems, they have a few knobs and dials that governance can turn. You definitely would need some tooling around here to generate your proposals and safely parameterize the system. So you could think about like the fee switch on Uniswap or the fee switch on Morpho or Euler, where they can set the fee. But then the rest of the system is immutable, so you can't actually upgrade the smart contracts. The third kind is a governance-heavy system. So in a governance-heavy system, the governors or whoever this trusted third party is, they can upgrade the contracts, they can change the system parameters, and to do this safely, there's a lot of times there's sharp edges with these kinds of code bases. So an incorrectly parameterized system can cause a lot of money to be lost. So lending markets, I think, and roll-ups are really good examples of these kinds of systems because there's a lot of knobs and dials. There's a lot of like different delays or collateral factors, interest rate models that have to be set. And these also tend to have upgradable smart contracts where the admin can come in later and make changes to things. Okay, so now let's talk about the security stack. So the hardest to find, I guess the most pernicious bugs, they're always the ones that no one is looking for. And when you're building contracts, a lot of blind spots will emerge because, let's say you're writing a new AMM, and there's some really complicated math formula. So you're saying, okay, let me make sure that, okay, the math here is like bulletproof, it's super solid, there's no issues. And so you spend all your time writing tests to make sure that your math is good. And because you're doing this, a simpler bug might just kind of slip through the cracks because you're spending all your time on this one thing that you think, oh man, this is like where the bug is going to be. Okay, I guess it just skipped ahead here. Okay, so there's, I'm just kind of skipping ahead now. Okay, right. So then also, let's say you're writing a lending market smart contract, then you're going to be spending a lot of your time on liquidations or reward logic or interest rate models. And then there's going to be other parts of the system that you're going to spend less time on. And again, that's another place where blind spots will manifest. So we can think of security for smart contracts as a stack. So we have all these different kinds of tools and techniques that we can throw at a smart contract system to try to find bugs. And at the very bottom of the stack, we can see the cost of finding bugs. So we can write fuzz tests, unit tests, integration tests. We can run static analysis. And this is like the cheapest way to find bugs. So you should invest in making a really solid test suite because that's gonna let you find all these things and find the bugs as cheaply as possible. So once you've exhausted like the really easy way to find bugs, you're gonna go and say, okay, well, let's get a little deeper. And so then you'll be going to something like symbolic tests. So that could be Halmos, that could be HEVM. There's a lot of different tools that allow you to do symbolic testing. So that will, give you certain, that will tell you certain things about the contracts that maybe your fuzz testing or your unit testing wouldn't find. Then you can go on to, formal verification, and you could use a tool like the Certora Prover or KEVM or Control, and those would find really, really hard to miss bugs, but they're definitely a lot more expensive to write a extensive suite, formal verification, like specification of your smart contract system than other testing methodologies. We also have code reviews, and code reviews are really great for almost just like rubber duckying things, right? Where you say, okay, you go through the code line by line and say, okay, what does this code do? What are all the assumptions? What are the upstream things? What are the downstream effects? And so those are great. Obviously, it takes more time to coordinate code reviews. Then we can go on to audits. So audits are going to be yet like an even more expensive way to find bugs, but you should definitely do that. But that's comes at the end of the development life cycle. And then we get up to bug bounties. And so the bug bounties, this is the most expensive way to find a bug in your system. You should definitely have this. It will give white hats an incentive to try to find bugs in your system. And then not pictured in this diagram, but it does happen, are black hat hats and that's the most expensive way to find out that you have a bug is to get all the money stolen. So it's definitely worth investing to make sure you don't get there. Okay, and so one thing that, is everything good? Okay. And the other thing is giving yourself space and time after you've finished building and you're at a code freeze or you've stopped major feature work. Oftentimes when you've really been like just throwing your head against the wall against a certain problem or a code base for a long period of time, you're going to be blind to the bugs that you've written. And so just giving yourself a weekend off or like just some time where you don't think, where you consciously don't think about the code you've just written, will give you the space so that when you do come back and you think about those problems again, then you'll be able to find bugs and come at it with a fresh perspective that you wouldn't have if you were just constantly trying to find the issues in the system. And during that period of time, when you come back, you can look for gaps in test coverage. You can look for things that you missed. Okay, so this is a quote from Tenet. No one cares about the bug that didn't get exploited, only the one that did. It's the bug that didn't get exploited, the danger no one knew was real. That's the bug with the real power to change the world. And I included this in the presentation because I feel like security, for the most part, is a very thankless job. Because when it doesn't work, you don't see it. And then, or when it does work, you don't see it. But then when it doesn't work, like everything has gone horribly wrong. And yeah, so that kind of leads us on to the bugs that we will, the bugs that regularly get missed. And so I think that a lot of times when we're talking about building new contracts, we'll be testing like all the new system components. But kind of the parts that get overlooked often are your deployment scripts and your governance proposals. So usually deployment scripts don't have tests. So this just means like there's basically just less eyes on things in general and less rigor than the rest of the code base. And I guess in thinking about this, if someone submitted a PR and had a whole new, a whole bunch of contracts and they didn't test it, you would say, well, wait a second, you need to write the tests. But somehow, when it comes to deployment scripts, we don't apply that same logic, which is not good. And I think the same thing goes for governance proposals. So governance proposals can be parameterizing and upgrading and moving things around in these systems that have all this money at rest in them. But oftentimes, we've actually seen where a governance proposal is not malicious, it just contains a logic error. And that logic error manifests in the system shutting down and not working as intended. So I think it's very important to test both of these things. And I think also one thing to call out is that like earlier stage projects, if you're a later stage project, you have the budget, you can go hire security researchers, and they can go and review all of your governance proposals. So that's good. But earlier stage projects often don't have that, don't have the resources to do that. So it's very important that you test these things. Okay. Wait. Can we transition the slides back to my machine? Okay. Yeah. Okay. So now we're going to give a bit of an overview of the Forge Proposal Simulator. So FPS is a tool that's built on top of Foundry. It offers developers a standard interface for creating their deployment scripts and governance proposals. And we treat these two things as one and the same, because a governance proposal might deploy a new smart contract and then wire that into the system, or upgrade a contract. And this framework makes it really, really easy to do integration tests on both your deployment scripts and on your governance proposals. So I think that this is like a really big unlock for projects where you have like governance-heavy systems and you're moving around a lot of knobs and dials and you're upgrading a contract here and turning a bunch of different knobs. So it lets you really easily connect your integration tests into your governance proposals. And so then you can say, oh, I already have written this huge integration test suite. And then with that integration test suite, you can run the integration test suite after the governance proposal is applied. So maybe you have like a bunch of invariants and a bunch of like states the system like shouldn't be in, or a bunch of behaviors that you would expect users to take. And then you can see, okay, if I do this governance proposal, are these invariants, are they still true? And then are these actions, are they still, like, can users still take them? Other features are we allow state diffing, so we can give you a full printout of everything and all those different contract states that changed, including like ERC20 token balance changes, Ether balance changes, and we also like help you manage addresses, and we have like a type system for addresses, whether they're like EOAs or contracts, so it can help you catch issues if your governance proposal accidentally talks to the wrong contract. Okay, so the first thing to cover is the addresses contract. So this is just a place to really easily store all of the addresses associated with your project, and then do type checking on them. So before you run a governance proposal or before you do your deployment script, you'll create a new instance of this address object, and then it will read in JSON files in your repository and store these addresses. And then it also does type checking. So if you say like, oh, this address on mainnet is a contract and this is its name, if you load that contract up and it is in fact not a contract, it'll fail loudly and it'll tell you like, hey, there's something going wrong here. And in the future, we want to be able to support actually like support like bytecode checking. So you could say like, oh, I expect this contract at this address to have like this bytecode, and then if it doesn't, you say, okay, there's something wrong, throw an error here. And so we can see on the right here, we have what this JSON structure looks like. So we just have some token addresses, and then then if you're like changing the addresses around, it doesn't need to like recompile your smart contracts. And then there's some more getter methods, like you can say, hey, is this an address a contract? Is this address on this chain a contract? And is this address like set? So do we actually have this alias? Is it used or not? Okay, and then we have a deployment script here. So we're gonna just go ahead and we're gonna say, okay, hey, do we already have this Bravo vault set in our addresses object? If not, we're going to go ahead and deploy a new one, and we're going to go ahead and transfer ownership to our protocol time lock. And then we have the same check for the vault token. We say, okay, hey, is it already deployed? If it's not deployed, we go ahead and deploy it. And this allows us to really easily like simulate. Let's say we have a governance proposal that needs to add a new contract to the system. This means that we don't need to like, in our test file, we parameterize and deploy this contract, and then, but then we have a different way that we actually deploy it in the real deploy script. Like we actually just get to combine our deployment script and our governance proposal into one thing, and our tests can go ahead and leverage that. And so this is the build stage. So this is some really cool stuff. So normally, if you're writing a governance proposal, you would have to like specify it in JSON, and you would say, okay, this is the target, this is the call data, and then this is the value, right? And now you read that in, and then it gets turned into whatever format that your governor expects. So maybe it's like a multi-sig, maybe it's a time lock, maybe it's a like Governor Bravo. But here, what we can do is we can actually write this governance proposal in plain Solidity. And the first step, we're just loading some addresses up so we can see like we use these keys, and the keys will tell us like will give us the addresses back. And then we start making the calls. So we say, okay, we need to whitelist the token, number one, we need to approve it, and then we need to deposit it to prevent maybe like a share price attack. And then what that does is, under the hood with Foundry cheat codes, it records all mutative calls. Okay. And all those calls then get translated into the governance type that you're working with. And this is completely modular. So whether you use a multisig, a time lock, Governor Bravo, or even your own completely bespoke system, all these components are really modular. You could just pull them off the shelf and use them to build whatever kind of system you want. And yeah, so we have support for Gnosis safes out of the box. We have support for OpenZeppelin time lock controllers. So that's like very nice to be able to just kind of like pull those off the shelf. We also allow you to generate call data. So we can have multiple developers. We can all be running these scripts locally and generating this call data and then comparing them when they go on chain. And the other really cool part is you can actually track proposals. So if you send a proposal to the DAO, and let's say your computer's been compromised and you send call data on chain, that's not what you expect because your computer's compromised. Then what can happen is your integration test suite can track the proposals that are on chain versus what you have locally in your repository. And it'll say, oh, wait a second, there were supposed to be 3 calls and they were calling the vault, the token, and then the vault again. But what's on chain is actually calling some other addresses, so we don't actually know what's going on here. So that can help you catch those kind of issues and governance attacks. Okay, and then finally we have the validate function. So this is part of the standard Forge Proposal Simulator just interface. So you can fill this out, and it works for both governance proposals and your deployment scripts. You just say, hey, here's these 2 contracts, the token and the vault, and maybe also the time lock that we touched in this proposal, and then say, okay, did this token actually get whitelisted? So we do like validations and make sure that the state is correct. Oh, did the balance of the vault change? Oh, is the total supply of the token what we expect? Is the token owner correct? Is the owner of the vault correct? And this allows us to validate both post-deployment script and post-governance proposal execution and see that everything looks exactly like we want it to. Okay, so now we're going to go to an example application. If you want to follow along locally, I'd encourage you to scan the QR code, or if you don't want to scan the QR code, you can just enter in the URL. I'll give everyone just a minute to get that pulled up. And so what we're going to do is there will be, we'll do a little code walkthrough here. We'll go through an example application, and we're going to go and try and find and fix bugs using this tool. And so we'll go ahead and start on Vault 00. So basically, you've been asked to build I guess this is kind of the specification of the system. You're building a vault contract that allows users to deposit tokens of the same value, and then they can withdraw those tokens at a later date. And so an example could be like you would whitelist, or you'd have a vault that's for WETH 8 and WETH 9, right? Just 2 versions of wrapped ether, let's say. And so then we would go ahead and create a vault with those 2 tokens. Let me go ahead here. Okay. So I guess we can start on the interface for the vault. So we have a deposit function, and we have a, it's a little small, we can make it bigger. So we have a deposit function, we have a withdraw function, you can specify a token, we have a list of authorized tokens here, and so you just pass in a token address, then it tells you whether or not the token is whitelisted. We then have the first governance proposal / deployment script here. And so we can, we have to do a little bit of setup here. We have a description. We have some other, setup items. And then we have our deployment script here, which goes ahead and, checks, hey, have we gone in, have we created this new vault with these tokens? And then we have the validate function. We're saying, hey, was USDC, DAI, and USDT, are they all deposited, or are they all like authorized tokens within this vault? So I'm going to give everyone just a minute or two to, I guess, think this through, look at the code, see if they can find any issues with it. Yeah, and then I'll take questions or answers from the audience. So here in the constructor, we go ahead and we set our authorized tokens. We have a deposit function where you can go ahead and deposit your tokens. We make sure that the token is authorized when you deposit it. And then we increment your balance, we increment the total supplied amount, and then we transfer the token from the sender into this vault contract, and we emit a deposited event. And then the withdraw function, we have a, pass a token, an amount. We have an implicit check here on the withdrawal. And then we also have integration tests here. So this integration test, we have all the different tokens that are deposited into this vault. We set some environment variables, and we go ahead and run the proposal. We deploy the contracts. And then we just go ahead and run the validate function. So we make sure that, hey, does it all check out? Does it do what we expect it to do? And then we have some integration tests here where we're actually running against a mainnet and saying, okay, can a user deposit DAI? Can a user deposit USDC? And can they deposit USDT? And then, okay, well, now that they've deposited, can they withdraw? And then now we have another use case where, we have someone deposits USDC and someone deposits USDT. And then, then each user decides that they want to withdraw a different token than they deposited. And so, making sure that those state transitions also work. And then we have a helper function down here. So has anyone been able to spot the bug? Okay, all good. It is a subtle one. So the bug in this system is, so the vault actually works fine for like-kind tokens, but it makes an assumption. And that assumption is that all vault tokens have the same denomination, the same decimals. It doesn't do any decimal normalization. So we have all these integration tests here, but unfortunately, they didn't test the one case that would have shown the bug, which is that if you deposit one DAI, you could just steal all the USDC, because it would be very unlikely that there would be, trillions or some huge number of USDC. and the contract. And so if we look at the deployment script, we have our tokens here, and the bug was in our deployment script. Like, we incorrectly parameterized this system. Okay. Just wait for this to. Okay. So, yeah, all the invariants that we would expect in this system, based on the vault and the total supply, all that works. But again, we have a bad deployment script. So, okay, we're going to go on to the next exercise now. Okay, so this next vault, we're going to just make things simpler here. So we have the same data structure. So this is all, we have a list of authorized tokens, we have user balances, and then we have the total amount supplied, across all the different tokens. And we expect the same invariance to hold from the previous vault, which is that the total supplied is going to be equal to the sum of the balance of all users, and that the sum of the balance of the vault of all authorized tokens should be greater than or equal to the total supplied amount. That's pretty simple. And now, instead of treating all tokens and not worrying about decimal normalization, we've added a decimal normalization function. And so here we deposit, we make sure, hey, the token is authorized. We pass in the amount. We then get the normalized amount based on the amount passed in. We increase the user's balance by the normalized amount, and we increase the total supplied by the normalized amount. And then we go ahead and transfer the tokens in. Nothing really changed there. We added an additional check, which in the first version of the vault, 0.0, we were able to withdraw an unauthorized token. And so while that wouldn't break the invariant, it would have been undefined behavior or something we weren't expecting. So we're just going to go ahead and add that in for just good measure. And so, yeah, we have our withdraw function here. And now we have our get normalized amount function. So basically, if the amount already has 18 decimals, we don't need to do anything. And then if the decimals are under 18, then then we need to normalize that up to 18 so that things just work. And we're going to say, hey, just for the sake of for the sake of this exercise, we're going to say that if you have more than 18 decimals, that's not in standard. We're not going to support that. But that is, that could be something that does happen. Okay. So now we're going to go ahead and take a look at our deployment script. So we allow USDC and USDT. I don't think we need to, use DAI. That's fine. We can just simplify things here. And then we have our validate function. And then we can go down to our tests. And so we just have USDC and USDT. And we go ahead and we have we test depositing, we test multiple users depositing, we test users withdrawing, depositing, and then withdrawing. We test 2 users are swapping, so one deposits USDT, one deposits USDC, and then they both withdraw the asset that they didn't deposit. And yeah, we still have this helper function, so that'll just help us out here. But I think there is a problem here. I think there's something there's something wrong somewhere here. And if anyone has any ideas, let me know. Okay. So the issue that we have here is of course the issue that we didn't test for. So if we take a look at the if we take a look at our deployment script here, we removed die. And because we removed die, if we would have run the validate function, we would have gotten an error that said, hey, die should be authorized. But we forgot to run that in our integration test suite, and so we didn't catch that there was like some discrepancy here between, oh, did we want to include it or did we not? And because we forgot that, because we forgot to include die in our test suite, then it meant that we didn't test any token that had 18 decimals, because USDC has 6 and USDT has 8, and we didn't test one with 18. But if we look at the Vault 1 implementation, we can see here that if the decimals are 18, there's nothing here that will handle that. So we would have a pretty big problem. And so that would mean if you deposited any amount of a token that had 18 decimals, you would get nothing. And this contract would then have your funds, which would not be good. So basically, because we didn't have a test here, and we forgot that in the deployment script, we missed out on like a pretty easy bug that we really could have found had we been looking for it. Okay, so now let's move on to the next version of the Vault. So we have some new requirements here. We need a way for the owner to add new tokens on the fly. And the business team said that they wanted a way to remove tokens as well, but you said, hey, look, sorry, if we, I can make this bigger if you want to read it. But if you said, hey, look, if we allowed you to remove tokens, then you wouldn't be able to withdraw because, anyway. So it would increase the complexity. You'd have all these different edge cases, and they say, okay, that's fine, but they just want to be able on a way to add tokens on the fly, and so we went ahead and we added just a single function here. The add token function, and then we went ahead and fixed the bug with the normalization. So the normalized amount starts off as the amount, and then if the decimals are under 18, we go ahead and handle that. Now, of course, we're assuming here that you're not going to have any like 19 decimal plus tokens, which I think is like a pretty safe assumption for most DeFi protocols. And there's actually there's no bugs here. And so then let's go on to the next contract. So now we need to make the contract upgradable. We need to preserve all the existing functionality. And we're not doing a forced upgrade because the previous contract it wasn't even upgradable, so we couldn't force the users into this upgrade if we wanted to. And so we would say, okay, users, you have to migrate into this by opt-in, so you have to remove your liquidity from the old contract and deposit it into the new one. And we're going to zoom out. Okay, so we have this contract here. Oh, this is the deployment script, so we can just go over that now. So if the Vault implementation isn't deployed, we go ahead and deploy it. We add it as an address. We whitelist all three of these tokens, USDT, DAI, and USDT. Our owner is going to be our time lock contract. Then we're going to go ahead and we're going to build the initialization call data for the proxy. And I guess the proxy admin now is created when you create the proxy. So we don't even need to worry about creating the proxy admin, but the proxy admin owner is set to the owner that you pass into the transparent upgradable proxy, so you just have to keep that in mind. Sorry. So we go ahead and add the address. We fetch the proxy admin from the proxy, and then we go ahead and add that to our addresses contract. Now we have our validate function here. So what this does is it makes sure that DAI, USDT, and USDC are all authorized tokens. It also makes sure that the vault, the proxy admin is the proxy admin owner is the compound time lock contract, and so that's the high level of our deployment script, and then we can take a look at the vault contract itself. So this contract is going to be, it has its storage in another contract, so that'll just go ahead and manage everything and keep the code clean for us. And yeah, then we have our events here. We pull our libraries in, disable the initializers in the constructor, so you can only talk to the proxy contract. We have our initialize function, our initialize modifier. We've added some events to just kind of make things easier, more, just give us some visibility into state changes when we initialize the contract. We've added a add token function and a set max supply function. So we've also added introduced a new variable into the mix, which is the max supply. So users can only supply up to the specified maximum supply amount. And only the owner can call this. Now our logic here for the deposit, it's unchanged, except we added this one new require, and we just say, hey, make sure that the total amount that you supplied plus the normalized amount, make sure that's not going above your supply cap. And everything else is pretty much the same here. It's the same contract, it's the same system, and our normalized function is fine. Everything looks pretty good, and there's not any bugs here as far as I can tell. Okay. So now some new requirements have gone ahead and come in again. So if we go to the exercise 4, the final exercise, we need to actually be able to make the contract pausable. But we also want to preserve all the previous functionality. You shouldn't be able to deposit when the contract is paused. But users should be able to withdraw their liquidity even if the contract is paused, and only the owner can pause and unpause. And then once we finish this implementation, we need to actually go ahead and upgrade. This is going to be like a forced migration where users of the old contract are now going to be forced to use this new contract. And if they don't agree with it, that's fine. They can go ahead and withdraw before the upgrade lands. So we can first start by taking a look at the deployment script. So we're going to go ahead, we set things up, we have our description here. The deployment is pretty simple because it assumes that we've already ran the third deployment script, which deploys the proxy admin, the proxy itself, and make sure that's all set up just right. And then, yeah, if this new v4 contract has not been deployed, then we're going to go ahead and deploy that here, and we'll add it to the addresses object. And now we're getting into the meat of the governance proposal here. So, we load up our different contract addresses here, and these are all static calls or calls to the addresses object, so they're going to get filtered out by the Forge Proposal Simulator framework. And then we go ahead and call the proxy admin, and we upgrade the Vault proxy contract to the v4 Vault implementation. And then we also need to set the max supply to some new number, so it's going to be 1 million. So that'll be like the supply cap in terms of this vault. So maybe it's a guarded launch, and we're only going to allow so many users to deposit. And then we have our validate function here. So we're going to say, okay, hey, our tokens, are they in the authorized list? Is our max supply, is that set correctly? Is our owner still the time lock? Because it shouldn't have changed, right? That should just remain static. And so now we can go over here. And so here we have a new storage layout. So that's the Vault Storage pausable contract. So that just extends the Vault Storage ownable and just basically just adds the new pausable contract at the end. And then we can go through this contract. So we still have the initialize function. Nothing has changed there. The constructor, everything's, that's the same. Our add token function, yeah, we still have that. Our set max supply, that's still in place. And then we have our pause and unpause functions. So only the owner can call these. And yeah, it's pretty, that's pretty simple. Our deposit function, yeah, you can only call it when it's not paused. So again, that's like a very, very small change. And then we have our withdraw function. There's no pause modifier on it. You can always withdraw. So, but I think there is an issue here, and we're gonna dig in. So we already have the deployment script. We have this build function. So here it's gonna, this framework, the Forge Proposal Simulator, it's gonna pull out all of this call data and package it up to talk to the Governor Bravo. And so that happens like all under the hood. It extracts these calls and turns it into a format that this DAO contract can understand. And then we're going to go to this test vault 004 contract. And this is going to, we have a setup function here where we deploy the SIP 03 so that we deployed the old contract versions. And we set up the proposal, we deploy it, we set the addresses in this contract to be the addresses that we already deployed, so we just like share a reference to that same addresses object. So we have all those addresses that have already been deployed here. We set our token, our stable coins, and we set our vault contract. I guess we go ahead and bump up the max supply as the owner, because why not? We set up the proposal. We deploy the contracts that are here. So we just go ahead and deploy the v4 Vault implementation if that's not already deployed. And then we're going to go ahead and we have like one test here, so we have to kind of figure out like what is the test that we should write that will catch the bug. But you can see there's nothing, and yeah, there's some things that are we don't have. So we don't really check any state of the contract, like what was this contract state before we executed this, and then what was it afterwards. And so basically, because we don't have any tests here, we don't really know what this governance proposal did. And I think there is, okay. It looks like some code got deleted that would make it easier to test this. But basically, there's the bug in this contract is actually, it has to do with the storage slots. So if you had deposited your tokens into the V3 of this vault, into the vault storage ownable, and then you deposited, and then the V4 upgrade happened, you got force migrated over. And so we have the ownable, we have the supply, but then the authorization and balances mappings got flipped in storage and how they were inherited. So the Solidity compiler just says like, oh, wait a second, the storage, the offsets are now different. And so that's actually in this, the fourth deployment script, because we don't have anywhere in the tests where we run this validate function, like a simple, like if we literally just said, if we just did that, that would give us a failing integration test, because it would say, wait a second, you've built this proposal and then you ran it, and then for some reason all of these tokens are no longer authorized. What's going on there? And so basically this would allow you to really quickly and easily catch bugs like that, because hey, all of the state of your system is just really easily available to you, and you can leverage your entire integration test suite to catch these bugs. And so maybe you don't even need to like write new tests, because you just say, oh, can a user deposit into this vault that I expect is authorized? And then, oh, for some reason you can't. And all of a sudden you're getting a revert that the vault isn't authorized. And so you say, oh, wait a second, there's an issue with the storage offsets. Okay, so yeah, so V4, the exercise 4, we had an issue in the storage offsets. So what did we learn from all of this? So you really have to use all of the testing methodologies that are available, starting from the bottom of the stack and then working your way up. So you start with the cheapest, you start with your unit tests, you start with your integration tests, and then you go to more expensive methodologies over time. And you'll always have blind spots. No matter how much you try to think about all the different edge cases of the system and all the different corner cases, inevitably there will be bugs, or there will be things that you don't foresee. And so that's where using a lot of different testing methodologies and a lot of different tools will help you find these harder to catch bugs, and getting auditors and the works involved. You should be aim to be as rigorous as possible. Think through all the edge cases. Think about your program as a finite state machine. What are the possible states it could be in? Do we have relationships between variables or invariants that we think should always be true? If so, how do we express that in a testing framework? Can we write invariant tests? Can we formally prove it? Can we use, how can we prove this to ourselves that this thing is true? And then, you say, we have these relationships between variables, but also you need to verify your state transitions, right? And make sure that, certain program states are unreachable, or certain, state transitions can't happen. And I think that there's really as the industry has progressed, we've invested a lot more in fuzzing and in formal methods and in test methodologies that really are good at discovering logic errors in code. And I think that as we've done that, and as we've gotten better and better there, our focus as an industry has gone away from these other kinds of bugs, which is why I think it's really important to also test your governance proposals and deployment scripts, and really get a lot of eyes there, because where attention kind of goes, that's where bugs disappear. And when you have all your attention in one place, then you have these other spots that, okay, hey, things kind of slip through the cracks. And then I think one final call out is that, you know, a lot of time should be spent on I think the majority of time should be spent on testing, and should be proving to yourself that, you know, this system really does what I think it does. Because if you're spending all of your time actually writing smart contracts, then you're going to get to the end and you're going to have a really buggy system, and there's going to be just a lot of things that you've missed. And so I think it's just really important to like be cognizant of where you're spending your time as a developer, and make sure that, you know, you spend a lot of time testing, and hopefully a majority of your time, because I think that's really the hard part, is proving to yourself that, okay, yes, this code that I've written is correct, and I'm like sure, you know, beyond a shadow of a doubt that like it does what I think it does, and there's no weird cases or corner cases, or if there are weird edge cases, I understand them. And so I think like a good test of that is like if you show up to an audit and you have a full specification sheet or a full sheet of all the edge cases that you already expect and know about your system. And so then that way, you know, it'll be easier for your auditors to like actually go and find the higher impact bugs. Okay, so if you want to use the Forge Proposal Simulator, you can scan this QR code, or you can go to one of these two links. So if you go to docs.soliditylabs.io, you can go ahead and, you can go and check out all the documentation we have on things. Oh, and one more thing. There is a state diffing feature in the tool. So if you can see here, so in the fourth proposal, we go ahead and we upgrade the contract, and then we set the max supply variable from 0 to, I think it was 1 million, or scaled to 18 decimals. And so if you look at the proposal changes, the Vault proxy contract had 2 changes. So the first one is it changed its implementation address. So it changed from the V3 implementation to the V4 implementation. And then the second one was the slot, I think the 0th slot, which would be the maximum supply. And so then you can see that it started off as 0, and then it got updated to 1 million. And that was, you can do that all from the command line. You just specify a few flags here. So you say, okay, run the proposal, print out the call data, and you know, we don't even need to run the validations here. Just print out the call data and show me the state diff of what I actually did. Yep, and you can feel free to stay in touch. I'm on Twitter at Elliot0x. My email is elliot@soliditylabs.io. And we are hiring smart contract engineers, so please get in touch. Thank you so much.
There won't be questions and answers. Yeah. Would you like to have questions and answers? We'll go on around and give the mic. 15. Okay.
Hear me? Yeah. Okay. Saudi Cup, everyone. I'm Jonatas. I'm really happy to make this presentation to you and share a bit about my process, how to leverage your knowledge and how to transition between blockchain stacks. I'm starting talking about me. So I've graduated in computer science. I've worked 5 years as web and mobile developer. During these years, I worked with PHP, React, React Native, and a lot of stuff. Right now, I'm 2 years working at Spearbit as associate security researcher. And one important migration between my career was I was working as React Native developer, and then appeared opportunity to start working as Flutter developer, and then I have only 1 month to change between stacks, and this, like, all of this experience brings me here to show you more about how can I use this process to learn new languages. So my proposal here is to get you a starting point to migrate your knowledge in Solidity and start learning Rust, and also do it fast, like not watching tons of videos and like lost too much time to make these kind of migrations. The agenda today I separated in 2 main steps. So the first one is the developer mindset. So we are going to check the difference between the blockchain stacks and understanding the code, then researching the framework, and then I will bring you a code here that we can read and understand the most of logic of it. And the next step will be the hacking mindset, so that you can use what you already learned in Solidity and bring it to the Solana blockchain. And the last one is the conclusion. So already starting the difference between like everything that you can see here, I didn't get it at the first moment that I start learning Solana. So it will happen like in a cycle, so you can get the basic stuff, and while you get deeper in the code, you can learn more. But just to bring you some basic stuff, like in Ethereum, you have one ETH they have 18 decimals, and one way is the last amount. In Solana, we have the sol, and they call it lamports, and have only 9 decimals. In Ethereum, usually you have only in the single code everything together, like the logic key and the data, where you can store everything. In Solana, we have 2 different types. So you have a logic program and a data account. Then in transaction in Ethereum, you can only call a single function, like when you send a transaction. In Solana, you can call multiple functions in the same transaction, use different signers. So have multiple signers as well. And in Ethereum, we have the precompiled contracts. In Solana, we call it a Solana program library. And it have the main basic contracts that you can interact, like to create token, some kind of this stuff. And in Ethereum, you have the self-destruct. Right now, it's changed a bit. But in Solana, you can also close and delete the account. So you have to close it properly and to not have any kind of issue. And another interesting stuff is that in Ethereum, you have the create2 that you can derive the account from it. You can predict the address of it. And in Solana, we have the PDA, which is the program, Let me close this. Okay, so we have the program derived address, which is the PDA. So usually when you want to create some data account from a program, you use this kind of structure. So starting already with the coding language. So in this step, you don't want to have a deeper understanding of how the Rust program language works. You just want to have like an overview of it. So you don't need to understand everything that you pursue. You can understand step by step. And we are going to do it by having it in parallel of how Ethereum works. So in Ethereum, we have the primitive types, that is the uint, int, address, boolean, bytes, this stuff. Then we have how to declare this variable. So we use this primitive type and then the name of the variable. Then we have this array type, how you use it. Probably you all know this, but it's how can you do it, compare everything. Then we have the array. Then we have the mapping that you can map an address to an integer, like checking the balance. A user could have. So we have this declaration. Then we have the structure type, where you can have like a person, car, or anything, and you have like the name. In this example, we have the name and then the age. So a person, you can declare a person like this way. We put the person P, and then the name, the age, and if you want to change, you can directly change the name just adding this. We also have the enum, which is just to add like a type to something and bring it to Rust. We have similar things. So we are going to have the primitive types. So we have U represents the uint, and it goes to 8 to 128. Then we have the integer, the Boolean, bytes. It's kind of similar. And how to declare a variable. So you use the keyword let, and then put the name. Then next is the type and the amount, and the value that you want. So if you want to declare an array, you need to use the let, and the mut keyword in this case is used to let the variable be changed. So in this case, if I want to add values to this byte variable, I will need to use the mut keyword. Then I can access any value and index in the array and can change it. Without this mut keyword, if you try to change the variable, you're going to get an error from it. We also have the structure types. So in this case, the user, you have like the Boolean active and the username. And this case is quite similar to Solidity, but the type is after when declared the variable name. Also, we can declare the user like this. You have the mut keyword again, and you set it. And if you want to change the username, we'll just add like this, the string from, and change it. We also have the enum. It's pretty similar too. And like you can add this deposit withdrawal types. So right now we just have like an overview of how Rust works, and you can already start read some code. But first, we need to learn how to declare and also use functions. So again, comparing the Ethereum and Solana, Solidity and Rust, we have like to declare a function, we have the keyword function, then the name of it. We declare the input type, so we have uint 256A and B. Then we have the visibility of the function, and if you want to return anything, you add the keyword returns and the type of returns, the type of it. And to return, we also have the keyword return and return the values, right? So to use this function, we can declare these two variables, A and B, and to use it, you just call the function and pass the inputs. Now take a look in the Rusty. We also have the visibility first, so it's a public function. Then we have the keyword fn, which means function, the function in Solidity. Then we have the name of this function. We have also the input type, so A and B, but it's quite similar. We add the type before of the name of this function. And to use it, you declare these two functions and just use normally like Solidity. So there isn't too much difference to get the basic knowledge of Rust. From now on, you can already identify some parts of logic of the code. And then there are also some different syntax from Solidity. Here we have the for and while loops. So in Rust, we can declare the for using this syntax. So we put the for and then the name of this variable and the range of it. And then we'll loop through this code. And the while is also quite similar. So you can see that you can just read everything normal and pretty understand it, the code. Okay, and we have the also if-else statement and the match. So the if-else, we don't use the brackets. We use the if keyword and then the cooperation, the statement inside to check if it's equal to something, and then else if, else. It's pretty straightforward, everything here. Then we have the match. The match is similar to the switch case, where you can see in some cases, so to match the number, if it's equal to 1, you have this print. If it's equals to 2, you have the another one. And in case of default, we have the another print. This and this. And now, like we have an overview of the code. We can already start jumping to the framework. We don't need to spend too much time studying complex stuff and know how to work and spend really much time understanding the language, watching videos, and all of this stuff. And we can check how the architecture of a program works. So we have the Foundry. In Foundry, everything can be found in these three folders. So we have the script to run, the tests, and the source. In the source, we will have the main logic of the code, right? So you can check here that we can declare a contract counter, which is the most basic contract here. So we have the number, and then this number we can just increment it. And we can also set it or anything else you can do in this code. We will do inside this contract, the counter contract, right? And okay, and now we can check how the Anchor framework works. So there is like a lot of files here. It seems like a mess at the first look. And looks like pretty complex if you don't understand anything. But if you can check this folder here, we can see that our program is defined inside it. So similar to the counter, we will have a source folder. We have the program. Then we have the name of our program, which is counter, and inside it we have the source folder, and inside the source folder we have the lib file. So the entry point of it, it's the lib.rs file. Then we have a bunch of code here also. You don't need to worry that you don't understand everything, because at the first time, as I said, we don't need to understand it. We just need to understand the logic about it. But to get a better overview, this rectangle will have the declare ID. In Solana is a little different because we define the public address before we create the program. So we add this value here. Then we have the program macro. A macro in Rust is it's like a function that will run background and make something easy to you, so you don't declare everything from the beginning, right? So we have our program counter here. In Solana, we also, as I said, we have the program and the data account. So we have to initialize this data account before using it. So usually when you start looking at the code, you will see an initialize function. In this case, we have the initialize counter function. And we also have the increment function here. As you can see, the inputs here, that's a lot of weird stuff, but we are going to check in a while everything. And we also have the inputs declared here, which is like the initialize counter. They have like a payer and the counter. So we are starting a data count called counter. And to use it, you have the struct called increment above, right? So the idea until here is to understand where we can find the files in the framework, because usually when we open a project, that like in a language that we don't know, we don't have any idea where to start and begin reading the code and check the entry points, all this stuff, right? Let me. So we have an overview of the project architecture and how to read some small pieces of code independently. And right now, my idea here in my process, before I understand the code and the file architecture, is to already start reading a code, like get vivid. Because when you read too much tutorials, you can spend too much time reading it, and when you go to a real case, the file architecture is completely different from what you see in these tutorials, right? So let me, where is my mouse? Okay. Right. So I got, I think you can see better now. So I got this code from a competition, a grass competition. They have 3 programs, but I think we can have time to understand probably 2 of it, or 1, I'm not sure. But we have the road staking and the token airdrop. So if you have an idea how a token airdrop works in Ethereum, usually you have a Merkle tree where you add all the user address and the amount of each user will receive from it. So the user, when called, it will prove that he belongs to that tree and will receive the rewards, and then they have a structure to mark that user already received this reward, right? And similar here, we are going to check it right now. So in this one, you can say that it has the program folder. Let me close this first. So you have the program script tests, also really similar to the Ethereum. Then we have the programs here. Inside it, we have our program, the token airdrop, and the folder source. So the first file that we need to check here is the lib, which contains all logic from it. So usually I reduce everything here because there is too much information when you start, and we don't want to get everything at first look. So here, this macro here is like to have the input type of the function. So we have this transfer CPI type, which is a structure that we can record here, the structure type. Then we have like a bunch of macros as the account here, but we can focus only on the variable's name here and the type of it. Similar what we look at the first slides. So we have the recipient, payer, and the system program. Which one, like when I have doubt about what this means and I don't understand it, I usually get back and search on the Google about it. So like if I want to understand what is the signer, you can go like to documentation on some video that could explain something and get back, like moving from searching and to already reading the code, right? So our main code here is declared inside the token airdrop module. Then also we are going to have here the initialize function which will initialize the Merkle tree, similarly which we have on Ethereum. Then we have the claim function, the set admin for this initialize data function, and lock claims in case you want to not enable to anyone claim the airdrop, right? So to understand a little bit more about the architecture, we are going to have the the instructions folder, which is the entry point of each function. So when you saw this, the folder named instruction, we have like each functionality separated by another file, right? And then we usually have the state folder, which contains the type of the data account that we want to store. So we will have, in this case, let me start from here. We are going to initialize a new Merkle distributor. So we have this function, handle new distributor. To this function, I will have this file, new distributor, and we have the data structure of this distributor here in a state. So in Solana, we have, for almost all the projects that use Anchor, this type of structure. Then we can see this function. We open the new distributor. We will find it here, right? So again, take a look. We have a bunch of declarations here. So the struct, initialize struct, then we have the new distributor struct. We'll have a bunch of macros. But again, we don't need to understand it. These are like helpers which will be checking some logic and will help you. Like, I don't need to check if the owner. I have a macro that help me to check this. And again, while you are getting deeper in the code, you are understand it more. But the idea here is to understand the logic of each function, and probably we may find some bug here. So to add a new distributor, we are going to put the version and the hoot. This is the Merkle hoot tree of this. As you can see here above, we are getting the distributor data count here. We are setting some variables to it. So we have the mut keyword. If we didn't have this keyword, probably the code will not work. So we add the version, the hoot, the minting, the token. We are like setting everything related to this distributor, right? And then we emit an event and finish. So this is initializing a new distributor. After that, we have set the data of this distributor, and any user can call this data and claim the tokens, right? So now we have the claim function here. So the user needs to pass the proof and the amount of tokens that he will get here, the allocation. Again, we have the handle new claim, and where we can find the logic of it, it's in the instructions. So the instructions here, you have the new claim, right? And you can jump directly to the logic of this function, which starts here, handle new claim. At this point, we can have an idea how to read the code, but we can also give a step further to it, so we can check like how this new claim struct is declared. So we have the distributor account, which is the Merkle distributor type. Then we have the claim status, if this account is already claimed, from, and then to, who is claiming, then the token program because Solana is different from Ethereum, so we need to call a program to transfer the tokens. And then usually you have the system program here. So again, the user passed the proof, the amount of allocation, and you can load the distributor, which we just created. Then the account which you claim, then this will verify the Merkle proof. You can also use the comments to help you understand something that don't make sense to you. And then we'll get the hash of the Merkle tree, and we'll check if the proof is added to the root of the Merkle tree. Then we have the status of it. There is one interesting thing because we can't store the data in the program, right? So we have the airdrop program here. We have the Merkle tree data, and we can't store the data of each user directly here. So you create another data extractor, which will contain if the user already claimed or not his. So you add the user info here, the claimant, and the amount of tokens that he is allocated to here. And then we have like this complex code here. We also don't need to understand, but it's like a token transfer. At this point, we just want to know that it's transferred tokens from probably the program to the user, right? And then emit an event from it. So we can also set the admin of the Merkle distributor, and we can also lock claims to this. So like check first the lock claims. So we'll have this function. So right here, we call the handle lock function. Then we can check here the client handle lock claims, right, function. Sorry. Then it's load again the distributor, and in the distributor you have the lock claims variable, and it will set to a Boolean that the user pass here, right? So it's the most easiest code that we could have in Solana, and it's not too much complex. So a user can claim, the admin can lock it, and you can also change the admin here to another admin. And while we get into the code, we can check like which is the signer of this account, and here we can check like if the admin, the past admin need to be different here in this case to set the admin, and then the admin could call this function, right? So in this code, we have a logic issue. If anyone could find it while you go just checking the logic, please get up your hand. No? It's like the logic here is you create the Merkle tree, you add the root to it, you can claim it, you can lock it. But if you can check when you claim it, there isn't any checks here to check if this distributor is already closed. So my idea here is that you can already start reading the code. You don't need to care about like what is macro, what is this context type and new claim type. You can take a look, like in this new claim, you have a bunch of variables, but if you can simplify, you could like remove this, remove this, remove this, remove this, remove this one, remove like every comment to make it simple. Then we have a structure type here. The structure is the new claim, and you have these variables inside it: distributor, claim status, from, to, the claimant, token, and system program. So you have an idea of how is the structure of this new claim, and then have this in mind. You will see like you're getting the distributor here, the claimant, which is already defined, then some logic to verify, again, the micro-root, the status, if already claimed or not. So you can already know the logic behind it. I forgot to pass about this state, but this state is here we can declare the data structure. So the new Merkle distribute will have this information inside it, the data count of it. And we could have also some implementations related to it, like if we want, we could add the logic here to verify the hash of it, and instead of declaring it here. Okay. Right. And I don't think we are going to have much time to like dive deep into the routing stake, but similarly, we can have this. Like this is a bit different from the other one. So let me close everything here. So we have the program, the token staking here, the source folder inside it. Then we don't have the state, but they declared here. So here we will find everything related to the pool. So this is a staking program. So similarly in Ethereum, we have the staking contract where the user put money on it and can withdraw money from it. So you have the same thing here. It's called the reward pool. So we have like these variables declared inside it and some implementation, as I said here, when you create a new one, then you can calculate the rewards of these. Then you have the stake pool, which also have some variables inside of it. And like I just got this code where I start looking at it, going to the lib file. So the lib, we have here the program name, and again, initializing the staking pool. You can transfer authorities like transferring the owner, adding a reward to that pool. You can deposit, claim everything, withdraw from it. In this one, we have the slashing function. So the user will stake, and in case it will kind of give him the voting power to an operator, and in case an operator does something bad, then it will slashing this. And like for each function, we have it separated here as well. We can like checking probably the deposit function, which is the easiest one. So we have the structure of the deposit. Again, with some variables, we can try to draw some diagram of it, adding every variables and have everything in mind. But the main function here is the deposit handle, right? You can find it here. So as you can see, this looks like pretty complex at the first time you look, but if you try to read each line and understand it every time, you're going to understand all the code, right? So the user here to deposit, he will add the amount and the lockup duration. Like I want to lock up my deposit for 1 week, for 1 day, for any time. So so you pass the pool that you want to deposit, right? And then it will load this pool, check the minimum time of this pool, and check if your time that you input is enough to add it. So it's really different from Ethereum. So we have the pool here, but when the user deposits, you don't start the data directly in the pool. Like for each user deposit, we're going to have a different data set for this deposit. That's why, because we create a new stake deposit receipt from it. And then we add the owner of it, the pool of the user is depositing, the payer, the amount of that user deposit, the effective stake, it's calculated here in this account, in this function. Then we have the lockup duration and the current time of this deposit, right? So I hope you guys understand like how to take a look at the logic. Although we don't have like any idea of how those things really works, just looking at it, you can start checking each line of this function. And as example, I'm not sure like what these things mean, like get effective. You can look at the code if you find this function in another place to understand it, or if you don't have it here, probably is something already predefined by the Solana program, and then you can just give a time from this code, get back to Google, search a little about how these things works, and then get back to it. This is usually my process of how to get a new understanding of new code. Like usually I don't spend too much time getting into tutorials, because what I've already noticed from all of my experience is after you watching like 30 hours of video explain some new language, when you go to some competition or trying to understand some new pattern, you will not remember everything that you have watched. So the idea is to get everything into practice, like, and get back, learn, and then practice reading the code, get back, learn, and do this loop until you can figure out how everything works, and with some time, you will get better, right? So for this, we look at real project architecture, know where is the entry point is located, and try to understand a bit of the logic of each entry point. And now with this, we finish the developer mindset. I do this loop until I can understanding all the code behind it. So like in this presentation, I can't dive deep more into too much details here, because we are probably spend some days trying to understand everything. Like I spent 1 or 2 weeks learning Solana and understand the code while I've participating in the grass competition, and I could find a medium issue which nobody found it. Then now we have an idea of how to read, how to get everything, and we could start developing our hacking mindset. So again, I have an idea of how Ethereum works. Like I know how the control access works in Ethereum, so the owner just can call some functionalities. We have the same thing here in Solana. If you take a better look at the macros, you can see that there is an access control to it. If you don't have it, probably you can break some of this functionality. We also have arbitrary calls. So when you pass in an account which you didn't verify it properly, you can make any call and calls to another data account and break it. In Rust, we also have underflow and overflow. So in most of the code, we are converting all the values and checking if we don't have any kind of this issue. And then we have also the project vulnerabilities. Like in lending project, usually you have a bad liquidation issue, and these kind of logic issues we can also find in Solana program. So you can reuse everything that you already know and try to find some vulnerabilities in this code. So we'll have like the lending staking program similarly. So we're going to have an incorrect reward calculations and incorrect liquidation, bad liquidation. And all of these logic issues, I put these in project vulnerabilities. And then we also have some Solana common vulnerabilities. You can easily check like Rust common vulnerabilities. You have a list of it. So Solana common vulnerabilities, Ethereum common vulnerabilities. And you can similarly take a look at these things. So in Solana, we have like, we can close an account. If you don't close it properly, you can revive this account. Example, the user called the claim in the Merkle distributor. So you add the value to it. You could also just close this data and like to not let the user reopen, but he could, if you don't close it properly, the user could reopen and can again some tokens. We have the account matching. Then when we are defining the structure, you have the type of this account. You don't have this type. So you can add any type of account to it and read, instead of you reading the owner, you are reading some hand-on value from it. We have the type crossplay and reinitialization attack. So if you search for it, we will find like 10 common vulnerabilities that you can already start finding it in Solana projects. So after that, we know that we could have the same issue in Solana. We have these common vulnerabilities, but from now on, how to improve my skills and get better on it. So during my process of improving it, I usually like to create diagrams of the project. So while I start a new competition, I start already drawing the diagrams and make all the flows, because when you're checking the logic, it's similar to Ethereum. So you have some flow that will broke. And then we can also learn some new patterns, like how is a project, a lending project in Solana. After you read a code, understand it, you can easily look at another code and matching those patterns. If the pattern don't match, probably one of them are incorrectly, right? And also searching for vulnerabilities. You can do it looking at Solidit site or looking at old competitions report. So we can also find all the vulnerabilities of a lending protocol searching for all the reports of lending protocol. You can have everything in mind, and then when you're going to make the next audit, you're going to find it faster. Also make POC, it's a good way. In Solana, I currently don't know how to make POC yet. I know how to understand the code, but because POC in Solana is different from Ethereum, like you don't use Rust, you use TypeScript. So it's completely different, and in my opinion, hard to make it yet, right? So doing POC, you can understand if like the flaw in logic you find, it's really a flaw. Because usually you see a lot of submissions that don't have POC, and there is pretty obviously, if you make one, you could find that is not an issue or it's an issue. And again, put everything in practice. I think this one is the best advice, because while you're practicing, and like I send one issue in a competition, and then I got a feedback there was 15 issues. So I learned from it where I don't find the issue, where to identify the code of this issue, and also have like defined description of how this issue works, right? So following this and having a loop of searching, understanding, you will improve all of your skills. And if there is one thing that I would like to guys remember from this presentation, is that you don't need to understand everything at the first time. You could, like, if you have a full-time job and want to make a competition to learn about Rust, you get one, try a little bit, understand some part of the code, some part you will not understand. But after putting everything in practice, with some time, like 1-2 weeks, you will see a good return of your knowledge. So that's it. Thank you very much, guys. I hope this presentation brings you new ideas how to improve it. And if you have any question, we can use it some minutes. No? Good. I hope I can explain better. Everything. Thank you very much.
Hi, it's very nice to have you here. And I want to ask a question. You mentioned about the Solana POC. So how do you fork a state of Solana and so that you can reproduce the hack?
All right, I've already searched about it, how to fork the state, and like, I don't think there is a way to do it right now. I think there is some complex steps that you need to do to fork a state and work on it. So like most of the POCs that I've checked, they create from zero. Like you have to declare everything, like to create a state and then use it to try to break it. So there is not an easy way that I can fork, like similar to Ethereum, you can just fork using Foundry and execute something in the contract. In Solana, you don't have it. So you have to code it to make it to that state yet. I think they are working to have something easier to do related to this.
Thank you, thank you.
Okay. Thanks.
Okay, so for the second to last talk of today, or workshop of today, I guess I'm deviating a bit from the topic of giving DeFi Security 101 introductions to like a level more meta. What I want to talk about is the Lean theorem prover. And you've seen Lean actually in the talk about control. And this is going to be like a more of a deep dive into the Lean theorem prover. And if you feel a bit tired, I can assure you I will do lots of live coding, and due to my state of mind, probably will make mistakes. Maybe that's going to be entertaining. So who am I? My name is Jacob. I work for a small DeFi company called Lindy Labs, and I'm basically working as a formal verification researcher there. My background is in type theory and in interactive theorem proving and in mathematics. And I'm the maintainer of Aegis, a small tool that we've so far only tested on our own source code. It's a formal verification tool that can be used to verify contracts written in Cairo. Cairo is the language that powers the Starknet L2. And if I have time, I will talk a little bit about Aegis at the end as some sort of example of what can be done using the Lean theorem prover as a basis. But since I was invited to give a general introduction to Lean, here we go first. So what is Lean? Lean is a project which has been founded in 2012, so roughly 12 years ago, by a guy called Leonardo De Moura, who had formerly been working on automated theorem proving. I think you saw the difference between interactive theorem proving and automated theorem proving in an earlier talk. And Lean is on the interactive side. It's dependently typed, which means that the return type of functions can depend on input values, broadly speaking. which puts it in the same class as other interactive theorem provers like COC and ACTA, if you know a little bit background. But if you don't worry. This talk will basically assume no pre-existing knowledge about interactive theorem proving. And it's both a functional programming language and a theorem prover. The theorem prover is written in itself. It basically compiles itself. And that makes it automatically makes it a good tool to deal with programming languages. And that's a bit of the gist of the talk that I'm giving, is that not only does it have like a proper good performance as a functional programming language, not only can you trust it to be correct because it has a very small and easily verifiable kernel, but you can also extend its syntax quite easily. And that's what we are going to do in this live coding experiment. And it's been designed with formal verification in mind, but also with formal mathematics in mind. I think the biggest user group of Lean is actually not people from formal verification, but it's mathematicians who want to verify their proofs. And that ranges from like super simple stuff to like the most abstract, complex stuff. And as I said, this talk is going to be like one step more meta than the previous talks. I'd say it's the perfect tool to build formal verification tools on. Barebone Lean itself is not a formal verification tool because it doesn't have baked in notions of semantics of various programming languages. So I guess I'll quickly go over some success stories of Lean. One success story being the so-called liquid tensor experiment, where a Fields medalist mathematician was not really sure about one of his proofs, which involved super technical arguments, and then called for help with the Lean community, and they managed to, within a few months, actually verify and simplify his proofs. And that's kind of been the starting point for many of mathematicians being inspired to use Lean. And then a few stories from this year. AWS, so Amazon, uses Lean to do a lot of things because like the main developer is now working at AWS. There's a certified differential privacy library in Lean, and maybe you've heard in the broader media of a project called AlphaProof. That's a proof tactic for Lean, which has been developed by DeepMind. That's actually been used to be so good at mathematic problems that it's actually solved a silver medal at the IMO, at the International Mathematical Olympiad, which, if you know anything about the IMO, is a pretty great achievement. The Lean ecosystem mainly consists of Lean itself, obviously, which, as I said, is self-bootstrapping, so it's written in itself. Then there's a standard library that's been managed by the Lean user community, which is called Batteries, because it's like the batteries included version of Lean. Then there's the big monorepo that contains most of the mathematics formalization, so that's called mathlib. It does have a good package registry called Reservoir, and it's called Reservoir because the package manager for Lean is called Lake. So far for the ecosystem. If you want to learn Lean, this hour obviously isn't enough to give you any more than just a glimpse of what you can do with Lean. It actually cannot serve as a tutorial with just so little time. But there's a few nice resources. There's a game that runs in the browser that's called the Natural Numbers game, which can serve as a first taste of proving statements with Lean in the browser without installing anything. So that's a first good step. And then if you're looking for more like proper documentation, there's an online book called Theorem Proving in Lean and one called Functional Programming in Lean, which respectively highlight the use of Lean as a theorem prover and as a functional programming language. And those two categories are not really distinct, because you can improve Lean's performance as a theorem prover by writing your own tactics, by writing your own automation. And so you can use the functional programming aspect to improve the theorem proving aspect, and you can use the theorem proving aspect to do something like verified programming, where the programs you write in Lean are actually correct by construction. Then there's a good textbook called Mathematics in Lean, which is obviously more aimed at mathematicians. And then I think the best resource for any kind of questions about Lean is Lean's Zulip server, which is just a huge beehive of activity. And I think it's the most active Zulip server in the world. And it should be the first point of contact for all kinds of questions you have on the Lean theorem prover. So yeah, like if I would give it like a credo in one sentence, I would say that compared to similar tools, Lean's strength is its extensibility for the syntax and its ability to pretty easily connect to external tools. And that makes it a good framework to write your own formal verification tools. And so what we're going to do today is to do a little bit of live coding. And different from the previous live coding demos that you've seen, I actually mustered up the courage to do it from scratch. I do have a GitHub repository where all the contents of this demo lie, and I will maybe revert to restoring some of the contents from this repo if my live coding deviates too much from the test runs I did before. So yeah, what's today's agenda is that we will look at a very small example language, not a language that you would want to write any programs with, embed its syntax into Lean, and then equip the syntax with a formal semantics, so with a meaning inside Lean, as a way to interpret the effect of those programs in the theorem prover. And then we will write a very, very, very simple optimization for the semantics, and maybe if the time remains, also verify a super simple program written in this language. Okay. So what does the language look like that we want to embed in Lean? Obviously, we don't have much time, so we can't look at a language which has like 100 constructs. So the statements of the language just fall into three categories. There's assignments, there's while loops, and there's if-else statements, as you can see with the two examples shown on the right. We just assume the memory to be flat, untyped, and mutable. So we just have for each string, for each variable name, we have one value. We have no types. Like we assume everything to just be like a 32-bit integer. And because we don't want to be writing down all kinds of binary operations, we just restrict ourselves to two expression formers, which are just, apart from obviously constants and variable names, a less than operator and an addition operator. And so what we'll do now is, we call this language imp because it's a small imperative language. And our goals are now to embed the syntax of imp into Lean and to implement and prove correctness of a small optimization. And to then be able to verify programs, we will also implement a big step, what's called a big step semantics for this language. If you don't know what a big step semantics is, no worries. You will basically see on this example what that means. Okay, so much for the slidey part of this presentation. Now, is this big enough? Is this big enough? Okay. So if you remember, the first bullet point was to define the syntax of imp. And what we want first to do is to define an internal representation of the syntax within Lean. That means that we will implement what's called an AST, an abstract syntax tree of this imp language. And this goes by the means of just defining inductive data types that consist of all of the elements of this language. Thankfully, there's only two basic constructs in the language, namely expressions and statements. And so we will have an inductive data type for expressions, which we call expr, and an inductive type for statements, which we call stmt. So inductive types form the foundation, besides functions, of Lean as a language. And if you're not familiar with functional programming, it's basically a generalized form of something like a struct or an enum, where you basically list all the ways of constructing terms for these types. And so for the expression data type, we want to list 4 of what's called constructors for this type. So remember that for the expressions, we have constants, we have variables, we have addition, and we have less than. That's all we need. I mean, we would need more to write a reasonable program, but that's all we want to deal with today. So let's first deal with constants. Let's just call the first constructor const. And now we have to list the arguments for this constructor. And const should just take a bit vector. And because we maybe don't want to repeat our basic data type again and again, let's define the type value as the type of bit vectors with 32 bits. We could also define like a programming language with infinitely large integers and so on, but okay, that's what we're going with in this example. Okay, so const should just take a value v of this data type. And then we need a constructor for variables, for named variables. And we just want to identify them by their variable name, so by a string. And now we need the 2 binary operations. And the trick here is that these form what's called recursive constructors. So we have one of them that's called LT, and that's got 2 arguments, E1 in expr and E2 in expr. So it takes 2 expressions as arguments. And the same goes for addition. Note that we will just implement LT as a operation that just spits out 0 or 1, just like in C, for example. Okay, so that's the data type for expressions. Now let's implement a data type for statements. The most basic building block is obviously an assignment, as we've seen here. Like all these lines that end with a semicolon and that colon equals are assignments. And what do they need? As arguments, they need a variable name on the left-hand side and an expression on the right-hand side. So we again give it an argument s as a string for the left-hand side and an expression for the right-hand side. And then we again need a recursive constructor because we need to cobble together several of these assignments or other language constructs. So we want to have a constructor for this sequential execution of 2 statements. So we have S1 in statement and S2 in statement. That will allow us to chain more than one statement together. And now we have if then else. That takes the condition, that's an expression, and it takes the then branch, that's a statement, and it takes the else branch, that's also a statement. And then we have while loops, which also take an expression, and the body, let's just call it B, statement. And now that we've defined these types, we can basically internally represent, for example, the assignment where we assign I to 0 by statement dot assign what did I do? And now if we hover here, we need a string here. So this would be I, and this would be 0. Oh no, this would be like the variable called 0. No, on the right-hand side, what we want a const. So. And because it can't derive the 0, we want to make this an abbreviation instead of a definition. Those are the details I actually didn't want to talk about, but those things happen when you do these kinds of things live. Okay, so this is what we want to represent a statement in the imp language internally. But we also really want to be able to write the syntax exactly in the way that I've presented it on the slides. And that's now where the extensibility of the Lean syntax comes into play. So the Lean parser is this huge, big thing that basically parses everything that I write into this editor. And we can extend it live as we are going. So we can extend the language that I'm using live, basically. And we first want to, for the parser, want to introduce new non-terminals for the parser. So we do that by declaring a new syntax category. And we just call them the lowercase variants of those two things. Like one we call expression and one for the statements. So that's new syntax categories. And now we want to basically look at this and basically just build a parser for each kind of language element in here. And we go through all of those 8 constructors now. Okay, let's start with expression. So the first 2 are actually, okay, I'll start with LT and with add because they're maybe a bit more intuitive. And we just write syntax and expression and a less than symbol and expression. That should be a new expression. And syntax, expression, and an add sign. It's a new expression. And now for the variable names, we just want to reuse the syntax category that Lean has for its own variable names. And we just do that by saying, okay, the identifier, which are called ident in Lean, should also be an expression. And we also want to use numerals. So we write num as part of expressions. Okay, so much for the expressions. Now we need to do the same for the statements. Okay, the assignment. What's it on the left-hand side? We have an ident, and then we have the colon equals, and then we have an expression, and that's a statement. And I'm actually lacking the semicolon at the end of the line. And the sequence is basically just a statement followed by another statement is a new statement. And the if then else, that's a bit of typing here. So we have an if, then we have an opening bracket, then we have the condition, then we have the then clause, which is a statement, and then we have the else keyword, and then we have curly brackets again, and then we have the next statement, and that should be a statement again. So that's been a mouthful. And the same for the while loops, the while keyword, and some curly brackets. The statement should also be a statement. Okay. Also note that this would be the point where, for the language, we would set the precedences of for example, for the addition. So we could determine whether the addition would be left associative or right associative, because we can write something like a binding strength here. Okay, so the next step might seem a little bit arbitrary, because now we can form all these expressions, but we want to have a way to reflect them back into a syntax category that's already used in Lean. So what we do is we write syntax and then we can basically turn every expression into a term. A term is the thing that the syntax category that Lean uses for all of the terms we can write down. And we do the same for statement. And what we can do now is let's check something like statement I : equals 0. And then that's already good because it already has parsed this. And now we get an error message that just says elaboration function for this has not been implemented. That just means that Lean doesn't yet, it can parse it, but it doesn't yet know how to equip it with any meaning that's relevant for Lean. We could also evaluate this and put it in quoting brackets. Why doesn't this work? Right, I wanted to evaluate this actually. Or let's not do this. Okay, so that's for the syntax. We saw the error message. So now we basically need to reflect the syntax that we declared to the abstract syntax tree. So this is our abstract syntax tree. And this is the syntax declaration. And now what we want to add is something called macro rules that basically take something of this form and turn it into a term like this. So for example, we match on a numeral. Then we just want to have expression.const and then how does this? Okay, now my stage blindness sets in. Okay, let's just start with a different macro. Let's start with the addition. So we want to move this to. Yeah. Now we need to surround this with so actually what I completely forgot is that we want to have the brackets around here. Minutes. And yeah, so I just noticed that this will take a while because for every constructor, I will basically now write one of these macro rules that will expand the minimal form into the full into the full form that's of any meaning to Lean. And so I just did the magic trick of restoring this to not waste too much time on this. So we see that for every of the language constructor, we have one of these macro rules. And now what we can do is, if we now check this, then we see that x plus y is less than z gets translated correctly to the AST. So these guard messages here are just a way to tell Lean that it should not output the actual output of the next command, but just should check that it actually matches what's in the comment above. That's actually quite a cool feature to embed test cases right in the file where you'd define them. So yeah, now we can write something like this in Lean. So we've actually, with just it's a 2-digit number of lines, we've just embedded a small imperative language as some sort of DSL inside Lean. Yeah, so we can write down programs and have a representation in form of this AST. Obviously, we still not really given it any meaning. So that's what we're going to do next. Let's next write a definition that actually evaluates an expression. So it's a function that takes an expression and should return something of the value. Why doesn't it? And since I restored this from the GitHub repository, I'm now at a version where I've not defined the value. So we do that again, value. Say that this is bit vectors of size 32. And actually needed this. And now we need to go through all of the constructors of expressions. So for constants, this is super easy because constants already have a value, and so we just evaluate them by returning this value. And then the next, let me leave out variables for a while and go to less and then. So less and then of x and y. And now we do a recursive call. So we just say that if eval of x is less than eval of y, then 1, else 0. Now it's saying, okay, there's 2 cases missing, the plus and the variables. Let's do the plus first. And that should just be like the evaluation of x plus the evaluation of y. And for the variables now, we noticed that what should we do with variables? And the way this is done is that we need a context of variables. So we need, for the evaluation, we need a mapping from the variable names to their value. And we can also, like with the value here, we can do a type definition and just say, we say that context, we can actually wrap it into its own structure and say it should just consist of a map for strings to value. So in a real programming language, we wouldn't just have a map here, but we would have something like a hash map because we will always only store finitely many variable names at each point. And now we can implement this. We can say that, okay, the variable should be, and now what do we have here? We still haven't any context, so the evaluation will always happen in some context sigma. And now we also have to retrofit the sigma everywhere. Okay. And now this might also be the point where we should define some operations on the context. So for example, getting the value given a variable name. Should be a value. And that should just be, because we need a context everywhere here. So we can just say, okay, this should be just be always, sigma should always be a context. So let's write this here. And this should just be the map that sits inside the context, and we should apply it to S. And likewise, we need something, we will later need something like set, where we can assign something in the context to a certain value. And so here, we need to say what the, this should be a new context. I shall say what the new map is, and this is just if, so for each, let's just call it S prime. So that's now a new string. And for each S prime, if it's the name we are overwriting, so if S equals S prime, then it should return V. And otherwise, it should look up in the context the term at S. Okay. And we'll just in a moment prove some our first theorems about like getting and setting variables in context. But let's first complete the definition of the evaluation here. Because now we have the context at our disposal. We have a variable name. Let's actually call it S, be a bit more consistent. Also, we've included this everywhere, so we can actually leave this out. No, wait, we can't. So we need to look up in the context. What's it as? But we need to look it up in the context called sigma. Okay, to test this, let's test this actually. We also want a function that basically initializes a context to a certain default value, maybe 0. Let's just pick 0, which should just be the context where for each variable name it should just be 0. And now it says, okay, we have not used this variable name. Lean is very strict about using every variable name, otherwise it will give you a warning. And now we can test this. Let's write eval of, so this is Lean's eval. This is now like, from a didactic teaching point of view, bad namings, but this eval is not this eval, but we want to evaluate the function called eval. What context do we want to have? We want the context.ini, in it. And now we have to give an expression. And we can use this dot notation when it's clear what kind of type a certain term should have. I hope you see that on the right-hand side. That's a very central point of almost all interactive theorem prover. It will show you the goal that we're about to prove when we prove something, and it will also show you the type of the holes that we've put into the editor on the left. Let's just add 5 to the variable I. And now we see that we've actually have the we have this bit vector as a result. So now we've interpreted the expressions in our programming language imp. So that's good. As I said, we might want for later purposes to actually have some theorems about getting and setting variables in the context. We might actually write our first lemma. And let's just call it context of get, set, same, which should just be a lemma that if we at the context sigma get s after setting s, so this should actually be sigma dot set s v. That should just be the same as v. What's happening there? Oh, that's all. Okay. And now we can type by, and that by keyword actually changes from Lean's so-called term mode to Lean's tactic mode. So here we will be able to write a sequence of what's called tactic. And tactics are basically a way of manipulating the current proof goal. So this is basically our proof obligation now. And every proof you will do in Lean basically consists of just a series of getting this goal closer and closer to something you can prove trivially. And in many cases, you will be able to just call the correct tactic and prove it in one step. I will not have the time to show you any very involved tactics today, but there's tactics which are basically implementing a best first tree search. There's tactics which do something like SMT solving. There's tactics that are AI-based and basically look at different proof structures and try to recreate the proof structure of your current goal. There's tactics that are very tailored to certain data structures. For example, whenever we want to prove something about rings, which is very important if you do any cryptography verification, there's very sophisticated tactics that just normalize a ring expression, for example. But so in this case, obviously, this lemma is super trivial. We will want to call a tactic called simp, which just simplifies stuff. And we can give it a list of definitions that it should unfold. So we just say, OK, unfold context.get and context.set. And then we get this good error message here, no goals to be solved. And with all of these interactive theorem provers, they don't necessarily give you like a oh, you solved all the goals message, but the rule is basically if your compilation in the IDE goes through, then you've manage to solve all the proof obligations. And then in Lean, you have something like, if we hadn't written this, we can write something like sorry, which basically tells Lean, okay, we are able to solve this, but we'll not do it now, we'll do it later. So yeah, that's our first theorem. And what we can do is actually tell SIMP to automatically apply this kind of theorem. And we can just annotate the theorem with SIMP. And now we will be able to solve any kind of, it will be able to reduce any of this term by just V. So yeah, you should always only do that if the left-hand side of an equality is like more complicated than the right-hand side of an equality. Okay, let me look at my curriculum. Yeah, the next step, I don't have much time left, but the next step would be, maybe I just restore everything and then I just walk you through the code. So yeah, we're now in the state where we've done all that. We've proven those lemmas, and now we want to write our first optimization. And that optimization, again, for the lack of time, can't do anything super sophisticated. But what it can do is something called constant folding. So if you have an expression that, for example, in a less than expression or in a addition has constants on both sides, it can just already pre-evaluate before running the program. And that's what constant folding does, and it actually propagates recursively this kind of optimization. It's a very weak optimization, but it's part of every good compiler. And so we can just define this as a recursive function from our expressions into our expressions that just does nothing on constants and on variables. And for example, on less than of x and y, it just recursively optimizes the left-hand side and the right-hand side and sees if both of them are constants, and then it replaces it with the final result. So this is already something you could call a compiler optimization. And now, obviously, what you want to do if you're writing a compiler, you might want to prove that it doesn't change the outcome. And for expressions, that would mean something like whatever environment we have, evaluating the unoptimized expression in this environment is the same as evaluating the optimized expression in this environment. And this, again, is a proof. So we can say by, and then we get a proof goal, which is just what we stated. And then we can call a tactic that's called induction, which just applies induction on one variable. And now we see that we not only got one goal, but we've got 4 goals that correspond to all of the 4 cases, to consts, variables, to plus, and to less than. And now we can actually act on each of these cases separately. So this would be a very structured proof where you can actually, you give case names, and then for each of those cases, you find ways to actually get rid of all of the goals. It's a bit like a computer game, and if you play something like the natural number game, you can see that this can be very addictive to just hack away proof goals. Obviously, this, again, is a pretty trivial proof, and you could also just solve this as a one-liner, either with a tree search or by just, for example, just concatenating several simplification tactics. So yeah, this is basically the proof that optimizing with the function that we've defined here doesn't change the value. Okay. So how do we give meanings not only to expressions but to entire programs? Let me introduce something that's called a big step semantics. So if you're familiar with formal verification or with programming language theory, you will already know this. But it's one way of giving meaning to programs that are potentially non-terminating, like the programs in our imp language. Because we could have non-terminating programs there. We can just have while one and then loop forever. And because Lean is a total language, we can't just write a total function which tells us what's the outcome of running this program in this environment, because it could never terminate and never give us an outcome. And so one way to circumvent this when arguing about proofs is to have an inductive predicate, so a predicate that takes an environment, which is being seen as the starting environment, the program, which is a variable of the type stmt, and an end environment. And basically, it's a statement. It's an inductively generated statement that tells you if I run this program in this starting environment, it will terminate in this end environment. And so this is an inductive predicate, so we will list axioms that will tell us several ways of proving something about this big step relation. So it's basically a relation with 3 inputs, like a starting state, an end state, and a program. And the constructors for this relation basically looks like something like this. If we start in a certain environment, then the skip program, which I've missed when I first did the syntax, I just noticed. Yeah, so we just missed the empty statement, the empty program, which is super important because otherwise you can't. Yeah. So if you have this program and you start with the state sigma, then you end with the state sigma. And for example, the sequential composition states that if you start in sigma and the program S1 brings you to sigma prime, then if a program S2 brings you from sigma prime to sigma prime prime, then the sequential composition of S1 and S2 brings you from sigma to sigma prime prime. Yeah, if you stare at it for a while, it seems reasonable. And the assignment basically says, okay, if you start in a certain environment, then the assignment has the exact effect of setting this variable in the environment. And here it actually calls the evaluation function that we've written for the expression. Then we have 2 cases for the if then else, depending on whether the evaluation of the condition is true or false. And then the semantics for the while loop are a bit more complicated. They have one easier case for the false case. So if we evaluate the condition and it returns 0, then the state before the execution of the while loop is the same as the state after the execution of the while loop. And if the condition actually evaluates to something which is not 0, so that means that we will execute one iteration of the while loop, then we can do something which is called loop unrolling, which basically says that if the body of the while loop brings us from sigma to sigma prime, and then the whole while loop brings us from sigma prime to sigma prime prime, and then the whole while loop will also bring us from sigma to sigma prime prime. Again, this is maybe a bit abstract, but it's the way you can prove things about while loops by continually unrolling single iterations of the while loop from the start. And you will also, like with contract, you will be able to not only prove statements about finitely many iterations of the while loop, but by induction you will also be able to prove what happens after an arbitrary, unbounded iteration of this while loop. let me just show you maybe this little example. It just happens to fit on the screen. So let's write a super simple program that just wants to swap the values that are in I and in J. I guess that's one of the first steps you would do in C or something like that as a kindergartner. And you would do that by taking a third variable, Z, and assign I to Z, and then I to J, and then you can assign J to Z. So you can actually do the swap by having one extra variable. And then we can, for example, prove that this actually swaps the two variables. So for every pair of environments, before and after the execution, and the statement, so this is a hypothesis. Lean doesn't make any difference between hypotheses and variables that you put as assumptions for theorems. So these are just two variables we want the theorem to depend on, and this is just a precondition, just a hypothesis we want it to depend on. So if swap brings us from sigma to sigma prime, then it will have the following obvious effect. If we probe sigma prime at I, we get what sigma gets us at J, and if we probe sigma prime at J, we will get what's previously been I. Let's make this a bit more transparent. So this is our proof goal, and so what we have to do is act on this hypothesis H. Let's first just unfold the definition of swap in H. And now we've seen that we have a little inline view of this little program here. And what we then can do is, again, this can all be automated, and it's just like for showing you what happens inside, is if you apply a tactic called cases on this thing, then it will look which of the cases that we've listed axiomatically above can actually be fulfilled in this situation. In this situation, the program just consists of a series of sequential assignments. So we can perform cases once. And now you see that here we got a new hypothesis, which just concerns the first line. And there we got a new hypothesis which just concerns the other two lines. And because Lean is very meticulous about variable names, it puts these gravestones to all of the variable names that we've not given an explicit name. And so we can perform these case destructions again and again. And then it gets very noisy here. If I do simp, it actually gets less noisy, but still a bit hard to read. And now this is actually a conjunction. So this is an AND statement. So you can write down constructor. And now we get two goals, one for the left-hand side of the AND, one for the right-hand side of the AND. And you can just call the simplifier, and it will actually prove that this actually is correct. Yeah, I guess that's as much live coding as you can do within an hour. Obviously, it wasn't all live coded. It was hilariously optimistic. But so going from a tiny toy language to an actual language which is used in DeFi, now that I've 2 minutes left, just skipping over really quickly. So Cairo is the function, as I said, that runs StarkNet. It compiles through an intermediate representation called Sierra, which has a very easy syntax, and it always compiles through what's called a single static assignment form. So we can very easily load this syntax, like we've seen today, into Lean. And I've actually written this Aegis tool, which basically just lets you type into Lean, okay, let's just load this Sierra file, and it then provides to the user commands that allows the user to give a specification, an arbitrary specification for each Cairo function, and to prove that this specification actually is correct. And by the end, you have something like Aegis complete, which is you put it down on the last line of your big theory file or of your number of theory files, and it basically checks that you've given a specification and proved a specification to every single function that your smart contracts includes. And we've actually dog-fed this to our own product. So this supports loops. It supports the syscalls in Starknet. And we've, let me end on this horrible slide. In terms of design, I mean, not in terms of content. So our own DeFi landing product has a white paper which lists a result from a mathematical branch called control theory, which basically implements a controller which determines a global interest rate modifier according to the formula you see in the first line here. You see that it's a nonlinear formula because it's got all these exponents and it's got square roots. And the white paper obviously implicitly assumes that we only deal with infinite precision numbers in this formula. And what we've done is we've actually managed to verify that if all of the variables which are in play here stay in reasonable bound, then the entire update operation, like this is an update operations which runs regularly on the contract, then the error, the numerical error of this is also bounded. And so this is the spec you see down there. And yeah, we're beginning to verify more of our own code, and we'll probably be ready to completely verify arbitrary Cairo contracts with this, and give it more assurances that I guess no other tool can actually give, because you can actually compare it to something like infinite precision numbers, and you can use the entire power of the mathematics that's been formalized in Lean to write your specifications and your proofs. And I think I'm over time, and thank you for listening. I'm happy to take questions afterwards.
No, it doesn't. Okay. Thank you. Hi, everyone. I'm here to show you a competition we're having at Satora during this DSS. So what we're having today and tomorrow and the day after that is a competition to build a smart solidity contract that matches our work in Satora, but in reverse. So usually what we do at Satora, we write CVL properties and CVL specification based on the code and design we get for our customers. It's hard to understand if it's easy or hard to start learning CVL. So we thought we save you the scary work of writing CVL and just do the other way around, and just you develop the smart contract, the solidity that everyone knows, and we bring the CVL for you. So we wrote the CVL for a smart contract that is a multisig, and you write the solidity. You just need a solidity contract that matches the spec, the CVL that we wrote. The spec is very easy to understand. It has properties of this contract. We have a solution, of course, don't worry. And you need to run the prover, and don't write any CVL. You don't need to write. You can write if you want. It's very nice, but you don't need to. So break nothing, as we like to say. The task itself, you get a repository. You get the link in a few minutes. It has a README. Please read the README. We worked hard on the README. It should have answers for all of your questions, and if there is something that is missing, there is a link there to lead you to a channel that has everything. So don't worry. You get a few files, multisig.spec, which has the rules that describe the flow of the contract of the system. We have an invariance.spec, which is another CVL file that has a lot of invariance of the system. For example, we have an array of validators. You will see in a few minutes. We want to verify that they are always unique, this array of validators. So one of the invariants is that all of the validators in any given 2 points are not the same, always. We have a sanity spec, which what it does is checks that you really implemented anything. And what I mean is that if you start with the empty implementation that you get from us, a lot of rules, a lot of properties will just pass. You can run it by yourself and see. And the sanity spec checks that you really implemented the features. Because otherwise, if you revert always, then there is no case in which the property broke, because nothing happens anytime. Nothing happens ever. So it just doesn't break anything, and it's not interesting. So that sanity spec is there to make sure that you're really doing something. If you want, you can just ignore it and see that you can implement something very stupid and it works. So we check it. We have the state.sol. Inside we have the storage variables, so you can have what you need to use during the implementation. For example, the validators array that I told about. And we have also something regarding transactions and more stuff there, so look there. We have the run.conf, that is just, don't need to change anything in it. That is the hard work we did for you, so everything is packaged, and just run Satora run and run.conf. And we have the empty contract for the multisig, which has only the external functions that should exist for you to implement, the API. And except from that, like, you can do whatever you want. You can write whatever Solidity code that you want. You can do whatever, just don't touch the CVL, because we will run it against our version of the spec, which is the one you get at the start, so don't change it. So we recommend you to write list of properties that is derived from the CVL. Like, for example, I said the validators array should be unique. More properties, of course, there will be more properties. But you don't need, like, if you don't want to, it's not a necessity. Like, you can do whatever you want, but we recommend it. Also, if you want, you can write a short description about what the system should do. It really helps to understand what should happen, and then you can start writing your code. It's like a real development process in really short amount of time. Like, in 2 days, you need to develop a system that is secure. The way we know it's secure is because of the CVL, and the way that we know it works is because of the CVL. So we should have everything, and it should show you that if we write a good spec, even before implementing, it should be very easy and very fast to just implement. And you don't need to, like, you should test also your code, but if you write proper rules, you don't even need to test it because it's already tested with the CVL. Then, of course, write the contract in Solidity and run the prover and see if you're right or not. So notes. Please read the README. I can't emphasize it enough. Everything is in the README. So the code needs to compile and have comments, so we can understand what you did. No bugs, of course. If we missed something or some property you think we missed, please send to us, but I think it should be fine. If something is not checked, then it's fair game. You can do whatever you want. I know that people here like to find vulnerabilities, so if you want to cheat, you can try to cheat. no hacking for other people, but everything that the prover says is okay, it's okay. So you can try whatever you want. I think we wrote a good spec, but you can challenge us and see if not. Of course, make the code as efficient as you can, because it will be important to us, but first of all compile, then pass all of the rules, and only then efficiency. So first security, then efficiency. So we have rules and invariants, as I said. Your solution shouldn't take more than 15 minutes. Our solution is faster than that, but it shouldn't take more than 15 minutes. And of course, again, don't change the spec file, of course. If you want, you can add more invariants to the spec file, like if you need them, because depending on your solution or your approach, you might need more. And you can add them and use them. That's OK. You can always expand our definition of the system or understanding of the system, or maybe we thought that we don't need this invariant or extra invariants, but eventually it turned out that we need maybe a more efficient version of the code that we can prove is correct. We still need those invariants to prove them. So if someone wants, feel free to add whatever you want, as long as it's invariant and you prove them. But we have a solution without additional invariants, so we have everything for you. You don't need to write CVL. If you want, you are invited to write CVL. It's similar to Solidity. OK, so this is the repo, if anyone wants to scan the QR. That's also the link. Give you some time. This QR should be everything you need, because the other QRs should be contained inside of this. So if I think everyone scanned, I'll wait another minute. OK. So this is for the support Telegram channel. If something is not contained in the README, the link for this channel is also in the README, so don't worry. And I just remembered that I didn't say about the, wait. Yeah, wait about, yeah. OK, all of the rules about the rewards and about everything is inside of the README, of course. As I said, everything is in the README. So good luck, everyone. Yes. Yes. So the reward is inside of the README, but I will say it so you will read the README. So the first three groups or individuals that submit a verified spec that is unique. So don't copy. Like if you submit a couple of times, we will just take the first one. So they win $1,000, and we have also a bonus for 3 rules that we have that we chosen. Like it's in the README also. The most efficient implementation of the code that will solve those specific properties fast, they will get $500. The fastest ones. So of course, in that bonus, of course, we also need to solve the other properties. Otherwise, it's just I'm not giving you the single rule to pass, and then you can revert, and that's it. So of course, we need to pass all of the rules, and if you're fastest in that specific rule, you get the bonus. You don't need to be the total winner to get the bonus. So good luck, everyone. And if for any other reason or for questions or for anything, if you want to reach me, and this is my Telegram, if you want. And that's it. Good luck, everyone, and submission until the 9th evening. Okay. Good luck.
Okay. How tired are you? Are you tired? Not yet. So tomorrow, first of all, thanks to all the speakers. Please, thanks to speakers for coming and presenting great material. Thanks to the wonderful volunteers helping us. Tomorrow we start early and we don't have breaks, so please sleep well. We start at 8 o'clock. I know it's a bit early, but we have to be out by 6. We have a lot of things. If you are a student or somebody who's attended this 101 and have a problem in getting a ticket for tomorrow, reach us. We can solve the problem. So please come on. If you have if you are here and a student and you attended 101 and you would like to attend the tomorrow and you don't have a ticket, don't worry. Reach out to the volunteers will help you. If you attended 101, we can give you a ticket. Enjoy and see you tomorrow.